Every moment, without pause, the universe stretches outward, unrolling mysteries so deep that they shake the very foundation of our understanding. What if life exists beyond the confines of our tiny blue planet? What secrets do the stars shining in the vast expanse hold about the birth of the cosmos and our place in this grand tapestry? Join us as we embark on a journey through the greatest enigmas of the universe. Among the most captivating phenomena we encounter are black holes, regions in space where gravity becomes so intense that not even light can break free. These cosmic giants form when stars, much larger than our sun, collapse under their own immense gravity. As they do, they warp space and time itself, creating a region beyond which nothing can escape, not even information. This boundary, known as the event horizon, marks a dramatic shift in the laws of physics. Beyond it, our current understanding of the universe unravels, leaving us with a web of unanswered questions. What lies within these dark mysteries? Can we ever truly comprehend the nature of these gravitational beasts? Another cosmic wonder that challenges our understanding is the phenomenon of neutron stars. These are the remnants of massive stars that have exploded in supernovae, leaving behind a dense, compact core. The density of a neutron star is so extraordinary that a sugar cube-sized piece of its material would weigh as much as all the humans on Earth combined. These stellar remnants defy our expectations, existing in a state of matter known as degenerate matter, where the protons and electrons have fused into neutrons. The intense gravity at play here also gives rise to pulsars, neutron stars that spin rapidly and emit beams of radiation. As they rotate, these beams sweep across space, creating the illusion of a pulsing light. Studying these strange objects forces us to challenge and revise our theories about matter and the forces that govern it. In the shadows of these phenomena lurks another cosmic puzzle: dark matter. This mysterious substance, which makes up approximately 27% of the universe's total mass energy content, remains invisible to our direct observation. It cannot be detected by light, but scientists infer its existence through its gravitational influence on visible matter. Dark matter affects the movement of galaxies, altering the way they rotate and influencing the formation of the larger structures we observe in the universe. Despite being such a dominant force in the cosmos, its true nature eludes us, forcing scientists to reconsider what we thought we knew about the universe. Could it be something fundamentally different from ordinary matter? Does it interact with regular matter in ways we've yet to understand? And then there's the mystery of cosmic acceleration. Observations have shown that not only is the universe continuing to expand, but its expansion is also accelerating. This discovery is both awe-inspiring and perplexing. To explain this acceleration, scientists have introduced the concept of dark energy, a mysterious form of energy that makes up about 70% of the universe's content. However, the true nature and origin of dark energy remain one of the greatest unknowns in modern cosmology. What is its role in the grand scheme of the universe? Does it hold the key to understanding the universe's ultimate fate? The mystery of dark energy fuels debates and drives research, challenging everything we thought we knew about space, time, and the forces that govern them. In this expanding universe, the discovery of exoplanets, planets orbiting stars beyond our solar system, has revolutionized our understanding of what's possible in the cosmos. For centuries, the idea of other worlds teeming with life existed only in the realm of science fiction. Now, with thousands of exoplanets discovered, many of which lie within the so-called habitable zone of their stars, the notion of life elsewhere seems increasingly plausible. In our own Milky Way galaxy, scientists estimate there may be as many as 100 million planets where conditions are just right for liquid water to exist, a fundamental ingredient for life as we know it. This realization expands our view of the universe, suggesting that life may be far more common than previously thought. The diversity of exoplanets we've discovered is staggering. Some planets are gas giants orbiting their stars in just a few days, while others resemble Earth, situated in just the right zone for life. These discoveries have forced scientists to rethink the models that explain planetary formation. They offer new insights into the diversity of atmospheres, terrains, and conditions in the cosmos. Each exoplanet provides a unique glimpse into how planets, and possibly life, form and evolve. As we continue to refine the technologies used to study these distant worlds, the quest to understand exoplanets stirs our imagination and beckons us to explore further. Galaxies, massive collections of stars, gas, dust, and dark matter are some of the most magnificent structures in the universe. These galaxies are categorized into three primary types: spiral, elliptical, and irregular. Spiral galaxies, like our own Milky Way, have well-defined arms that spiral outward from the center, often containing young stars and abundant gas and dust. This structure promotes the continuous formation of new stars and nebulae. Elliptical galaxies, in contrast, have a smooth, rounded shape and are made up mostly of older stars with little gas or dust. These galaxies tend to be more peaceful, with minimal star formation taking place. Irregular galaxies defy categorization, appearing chaotic and often hosting large amounts of gas and young stars. These galaxies are frequently involved in gravitational interactions with nearby galaxies, which trigger bursts of new star formation. The formation of black holes begins when massive stars run out of nuclear fuel. With no energy to counterbalance the pull of gravity, these stars collapse under their own weight. In a dramatic finale, the star explodes in a supernova, casting its outer layers into space. What remains is a core so dense that it collapses into a singularity, a point of infinite density. The boundary surrounding this singularity is known as the event horizon. It marks the point of no return, beyond which nothing, not even light, can escape. The study of black holes is an ongoing challenge to our understanding of the laws of physics. They bring together the forces of general relativity and quantum mechanics, two realms of physics that, so far, remain irreconcilable. What happens inside a black hole? Does time and space, as we understand them, cease to exist? These questions remain unanswered, keeping scientists and astronomers at the edge of discovery, exploring the ultimate unknown. In the grand scale of the universe, black holes, neutron stars, dark matter, and cosmic acceleration are just a few of the vast mysteries that challenge our understanding. The universe, constantly expanding and changing, holds secrets that may never be fully unlocked. Yet, as we continue to observe, discover, and question, we inch ever closer to understanding the awe-inspiring phenomena that shape our reality. Each discovery leads to more questions. Each answer unravels a new layer of the cosmic puzzle, inviting us to keep exploring the boundless wonders of the universe. Black holes come in various sizes, each with unique characteristics and implications for the universe. Stellar black holes, which form from the remnants of massive stars, are relatively small compared to their supermassive counterparts. The latter, containing millions or even billions of solar masses, reside at the centers of most galaxies. These incredible phenomena challenge traditional scientific understanding, but their significance reaches far beyond just being cosmic anomalies. Black holes are crucial players in the evolution of galaxies, influencing their formation and growth. The role they play is fundamental, as their gravitational forces interact with the surrounding space-time, shaping galaxies in ways that are still being unraveled. The search for a deeper understanding of black holes has propelled much of modern astrophysical research. Researchers use advanced techniques such as gravitational wave detection and imaging to observe these enigmatic objects. The Event Horizon Telescope, for instance, captured the first ever image of a black hole's shadow in the galaxy M87. This groundbreaking discovery revealed an awe-inspiring, blurry ring of light that is not the black hole itself, but the bending of light around it. Each of these discoveries builds upon the last, gradually piecing together the vast puzzle of the cosmos, where forces far beyond our current comprehension are at work. These cosmic forces challenge our understanding of physics and the very nature of the universe itself. In parallel with black holes, dark matter emerges as another profound mystery that shapes the architecture of the universe. Although invisible and impervious to light, dark matter exerts a powerful gravitational influence on visible matter, which is how scientists have inferred its presence. Observations of galaxies show that they are surrounded by enormous halos of dark matter. This unseen mass significantly affects their structure, behavior, and evolution, and without it, many of the galaxies we see would not function in the way they do. For example, the rotation speeds of stars in the outer regions of galaxies defy the predictions made based solely on visible matter. This discrepancy points to the existence of additional unseen mass whose gravitational effects hold the galaxies together. Dark matter is especially crucial in understanding the formation of galaxies. In the early universe, regions with higher concentrations of matter began to collapse under the force of gravity, forming the first galaxies. Dark matter played a central role in this process, acting as a cosmic scaffolding around which regular matter could clump together to form stars and planets. This gravitational framework also facilitated the formation of larger structures in the universe, such as galaxy clusters, providing the necessary conditions for them to come together and evolve. As our understanding of galaxies deepens, so does our recognition of dark matter's influence on galactic dynamics. When examining the rotation curves of spiral galaxies, scientists find that the rotational speeds of stars in the outer regions do not match predictions based solely on visible matter. This is clear evidence that there is more mass present than can be observed, mass that we cannot yet directly detect. Dark matter's gravitational pull is essential for maintaining the structure of galaxies over billions of years, preventing them from flying apart, despite the high speeds of stars within them. Dark matter also plays a pivotal role during galaxy collisions. These colossal cosmic events are not only shaped by the visible matter within the galaxies, but also by the dark matter halos that envelop them. As galaxies merge, their dark matter halos interact, influencing the final outcome of these encounters and shaping the evolution of the resulting galaxies. These observations underscore the critical role of dark matter in the ongoing evolution of galaxies, while highlighting the profound mysteries it continues to present to astrophysicists. While dark matter remains one of the universe's greatest enigmas, dark energy adds another layer of complexity. At first glance, dark energy might seem almost impossible to detect. It doesn't emit, absorb, or reflect light in any way. Yet, its presence is inferred through its gravitational influence on visible matter, radiation, and the very fabric of the universe itself. Dark energy is believed to be responsible for the accelerated expansion of the universe, a discovery that has prompted a revolution in cosmology. One of the most effective ways scientists study dark energy is by observing distant supernovae, the explosive deaths of stars. These supernovae serve as cosmic beacons, or standard candles, that provide critical data about the universe's expansion. By analyzing the light emitted by these stellar explosions, astronomers can compare the observed brightness with the intrinsic luminosity of the supernovae, helping to measure the rate of the universe's expansion. The results consistently show that the expansion is accelerating, a phenomenon that can only be explained by the presence of dark energy. The ongoing pursuit to understand dark energy is reshaping our understanding of the universe. It forces us to reconsider the very nature of space-time, pushing the boundaries of physics and cosmology. As we look deeper into the cosmos, both black holes and dark matter reveal themselves to be key components of a universe that is far more intricate and mysterious than we ever imagined. Each discovery, whether it be the capture of a black hole's shadow or the observation of distant supernova, brings us one step closer to understanding the forces that govern the vast expanse of space. The more we uncover, the more we realize just how much we still have to learn. Large-scale surveys of the cosmos, like the Sloan Digital Sky Survey, have become essential tools in our quest to understand the universe. These surveys meticulously map the positions and brightness of millions of galaxies scattered across the vast expanse of space. By analyzing how these galaxies are distributed and how they tend to group together, researchers can draw profound conclusions about the influence of dark energy on the evolution of cosmic structures over time. The galaxies' clustering patterns provide a key to understanding how dark energy has shaped the expansion of the universe. An important phenomenon tied to this process is the observation of baryon acoustic oscillations, a signature pattern of regular fluctuations in the density of the universe's matter. These oscillations serve as yet another powerful tool in revealing the influence of dark energy. They help us understand how this invisible force continues to shape the fabric of the cosmos, adding to the cosmic puzzle that scientists strive to solve. Moreover, the cosmic microwave background, CMB radiation, holds a pivotal place in astrophysics. This faint glow is a relic from the earliest moments of the universe, an afterglow from the Big Bang. Subtle variations in the CMB radiation offer crucial insights into the conditions that prevailed when the universe was just a few 100,000 years old. By studying these minute temperature fluctuations, scientists can uncover vital information about the density and composition of the universe, including the proportions of dark matter and dark energy. These insights provide a glimpse into the very makeup of the cosmos, allowing us to piece together how the universe has evolved into what we observe today. The convergence of these methods, coupled with the power of advanced simulations, enables researchers to begin unlocking the mysteries surrounding dark energy. Together, these tools help us chart the expansion of the universe and may one day reveal its ultimate fate. Then there are the gravitational waves, ripples in the very fabric of space-time itself, produced by the most violent and energetic events in the universe, such as the collisions of black holes or neutron stars. Albert Einstein, in his groundbreaking general theory of relativity, first predicted these waves in 1916. His theory described how mass and energy warp space-time, suggesting that massive objects could create disturbances that propagate across the cosmos. The profound significance of gravitational waves lies in their ability to reveal phenomena that are otherwise invisible to us. Unlike light waves, which can be blocked or absorbed by matter, gravitational waves pass through everything undisturbed. This unique property enables scientists to study celestial events that were previously beyond our reach. The detection of gravitational waves has thus heralded a new era in astronomy, known as gravitational wave astronomy. By observing these waves, astrophysicists can gain insights into cosmic events such as the merging of black holes or the life cycles of massive stars. The first successful detection of gravitational waves in September of 2015 was a monumental achievement. The Laser Interferometer Gravitational Wave Observatory, LIGO, detected waves from the merger of two black holes located more than 1 billion light-years away. This discovery not only validated Einstein's predictions, but also opened up an entirely new way of observing the universe. For the first time, we were able to observe the collapse of two black holes, each around 30 times the mass of our Sun, spiraling together and merging into a larger black hole. This milestone sparked excitement across the scientific community, showing that gravitational waves could offer a unique lens through which to study the birth and evolution of black holes, as well as the intricate dynamics of cosmic objects. Since that momentous event, the ability to detect and analyze gravitational waves has expanded. Additional observatories and instruments have joined the effort, helping to uncover more about the hidden depths of the universe through these faint ripples in space-time. Another fascinating phenomenon is the existence of rogue planets. These are planets that roam through space without being bound to any star. Unlike the planets in our solar system, which orbit the Sun, rogue planets may have once formed around a star before being ejected due to gravitational interactions with other celestial bodies. Some scientists speculate that rogue planets could be as numerous as the stars themselves, offering a new and surprising perspective on planetary systems. The mechanisms behind the ejection of rogue planets are compelling. During the chaotic early stages of a solar system's formation, young planets often collide or pass close to one another, altering their orbits in dramatic ways. With enough energy from these interactions, a planet can be flung into interstellar space, detached from its original star. Another possibility is that rogue planets form independently, far from the warmth and light of any star. These planets may coalesce from the cold gas and dust drifting through space, eventually becoming solid bodies despite the lack of nearby stellar radiation. Studying rogue planets is a challenging task due to their solitary nature and the lack of a star to illuminate them. However, recent advancements in technology have enabled scientists to develop new methods for detecting and observing these elusive objects. By studying rogue planets, researchers hope to learn more about planetary formation in distant and isolated regions of space. Furthermore, these planets raise intriguing questions about the potential for life in places far removed from the warmth of a sun. Supernovae, the explosive deaths of massive stars, represent some of the most extraordinary cosmic events. When a star runs out of nuclear fuel, it can no longer support itself against the force of gravity, leading to a catastrophic collapse. The result is an explosion that is not just visually spectacular, but crucial for the synthesis of elements necessary for life. During the extreme heat and pressure of a supernova, new elements are forged in a process that creates heavier elements like carbon, oxygen, nitrogen, and iron, elements essential for life as we know it. These elements are not confined to the explosion itself. Once the supernova has finished its violent display, the debris is dispersed throughout the cosmos. This material enriches the surrounding interstellar medium, providing the building blocks for new stars and planets. It is within these newly formed celestial bodies that the elements created in ancient supernovae come together, laying the groundwork for the conditions that support life. Without these cosmic explosions, the universe would lack many of the elements essential for life, both on Earth and possibly elsewhere in the cosmos. Finally, the cosmic microwave background, CMB radiation, serves as one of the most extraordinary windows into the universe's infancy. This faint glow, which permeates all of space, originated about 380,000 years after the Big Bang, a moment when the universe cooled enough for atoms to form. At this time, the universe became transparent to radiation, allowing light to travel freely for the first time. The CMB we observe today is a snapshot of that moment, offering us a view of the temperature fluctuations that would eventually give rise to galaxies and clusters of galaxies. These tiny variations in temperature are not mere noise. They provide vital clues about the early conditions of the universe. They reveal information about the density of matter and energy during this pivotal period, shedding light on the composition of the universe, including the proportions of regular matter, and dark energy. Strikingly, maps created from CMB data suggest that over 70% of the universe is composed of dark energy, a mysterious force that is driving the accelerated expansion of the cosmos. Together, all of these observations, ranging from the distribution of galaxies in the cosmic microwave background to gravitational waves and the life cycle of stars, allow scientists to gradually uncover the secrets of dark energy and the evolution of the universe. These efforts may eventually lead us to understand not only how the universe began, but also how it will evolve in the distant future. The cosmic microwave background, CMB, continues to challenge our understanding of the universe, posing profound questions about its geometry and fate. The data suggests that the universe on a large scale is remarkably flat. This observation has sparked intriguing debates about what lies ahead for the cosmos. Will it continue expanding forever, stretching into an infinite void, or is there a possibility that it will one day collapse, contracting upon itself in a cataclysmic reversal of its current trajectory? Each discovery related to the CMB unravels deeper layers of complexity and adds richness to our understanding of cosmic evolution. This faint ancient radiation holds clues not only about the early moments after the Big Bang, but also about the very laws that govern the universe's existence. As scientists study the CMB's intricate patterns, they also delve into the mystery of cosmic inflation, the rapid expansion of space that is believed to have occurred in the split second after the Big Bang. The subtle fluctuations within the CMB may hold the key to confirming this theory, offering insights into how the universe evolved into a structure capable of fostering galaxy formation. Yet, the CMB is not just a relic of the past. As scientists continue to analyze this faint glow, they are peeling back the layers of the universe's infancy, opening doors to new understandings that could reshape how we perceive the universe. The study of the CMB pushes us to ask fundamental questions about the nature of space and time, the origin of cosmic structures, and even the ultimate fate of all that exists. String theory offers a daring attempt to unify the fundamental forces of nature, challenging everything we know about the fabric of reality. At its core, string theory posits that the fundamental building blocks of the universe are not point-like particles as traditionally believed, but tiny vibrating strings. These strings vibrate in different patterns, and each vibration corresponds to a different particle, suggesting an almost infinite array of possible ways matter and energy could behave. If string theory is correct, it would present a radically new way of understanding the universe, providing a framework that could reconcile two of the most powerful and incompatible theories in physics, quantum mechanics and general relativity. Quantum mechanics, which governs the behavior of subatomic particles, and general relativity, which describes the forces that shape space and time, have long been seen as incompatible. String theory offers the tantalizing possibility of reconciling these two pillars of physics, suggesting that they are simply two sides of the same coin. By merging them, string theory could provide profound insights into the very structure of space-time, potentially revealing new dimensions beyond the familiar 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. This notion of extra dimensions is not merely a theoretical curiosity. String theory suggests that these dimensions could play a critical role in the fundamental workings of the universe. In fact, some versions of string theory propose that our universe may be just one among many, each with its own distinct set of physical laws, existing alongside an infinite array of parallel realities. This multiverse concept raises deeply provocative questions about the nature of reality, challenging our assumptions about existence and offering new avenues for exploration. Moreover, string theory hints at the possibility that the 4 fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, may be different manifestations of a single underlying principle. If this idea holds true, it could revolutionize our understanding of the universe, revealing a unified theory that connects the fundamental forces that govern everything, from the behavior of subatomic particles to the movement of galaxies. This potential unification would not only change our scientific worldview, but also illuminate the hidden threads that weave together the grand cosmic tapestry. Each new revelation in this field brings us closer to understanding the origins and inner workings of the universe. These discoveries remind us that we are still on the cusp of understanding the full depth of cosmic history and the laws that govern the very fabric of reality. Yet, even as we venture deeper into this fascinating journey, we find ourselves standing at the threshold of one of the greatest scientific mysteries of our time: the possibility that our universe is just one of countless others, each with its own distinct history and set of rules. The theory of the multiverse adds another layer of complexity to our understanding of quantum mechanics, which is itself a realm of baffling paradoxes and mysteries. Central to quantum mechanics is the concept of superposition, where particles exist in multiple states at once, only deciding on a specific state when they are measured. This strange phenomenon has given rise to a host of interpretations, as it appears to challenge our everyday understanding of reality. According to the multiverse theory, when a quantum event occurs and a measurement is made, the universe does not collapse into a single outcome. Instead, it splits into multiple realities, each representing a different outcome of the event. In this view, all possible outcomes of a quantum measurement are realized, but they occur in parallel, non-interacting universes. For example, when a particle is measured, one universe would emerge where the particle takes one specific value, and another universe would form where the particle takes a different value. This idea forms the basis of what is often referred to as the many worlds interpretation of quantum mechanics. As such, the multiverse theory proposes that the universe continually branches into countless realities, each corresponding to a different version of events. This concept challenges our conventional understanding of reality, suggesting that our universe may not be the only one, and that an infinite array of parallel worlds exists, each following its own distinct path. Many physicists see this interpretation as a potential solution to the measurement problem in quantum mechanics. The measurement problem centers on the fact that quantum systems behave differently when observed. Without observation, particles exist in a superposition of states, but once measured, they collapse into a single definite state. The multiverse theory resolves this dilemma by proposing that, rather than collapsing into a single outcome, the universe splits into multiple realities, each corresponding to one possible outcome. Despite its compelling nature, the multiverse theory has its critics. Many point out that it remains speculative and lacks empirical evidence. There are concerns that it may complicate our understanding of quantum phenomena rather than provide clarity. However, the theory continues to intrigue scientists and philosophers alike, as it opens up new possibilities for understanding the strange, counterintuitive world of quantum mechanics. It forces us to reconsider the very nature of reality, pushing the boundaries of what we know, and inviting us to explore the possibility of an infinite number of parallel worlds, each with its own unique history and future. Lastly, the idea of time travel has fascinated humanity for centuries, stirring imaginations and sparking theories that stretch the limits of our understanding of the physical world. While the notion of traveling through time may seem like pure science fiction, advances in theoretical physics have suggested that time travel could, in principle, be possible. The theories surrounding time travel often draw upon the complex and mind-bending ideas of relativity, quantum mechanics, and even the mysterious nature of space-time itself, further expanding our understanding of the universe and its possibilities. Time, a concept so deeply intertwined with the fabric of the universe, remains one of the most elusive and enigmatic aspects of reality. One of the leading theories regarding time travel is rooted in the very fabric of space-time itself, a four-dimensional continuum that binds the three spatial dimensions, length, width, and height, with the fourth dimension, time. Albert Einstein's theory of relativity tells us that as objects move closer to the speed of light, time behaves in unexpected ways. Time, in essence, dilates. It stretches and slows down for those in motion compared to those who remain stationary. This dilation is not just a theoretical concept. It is something that has been experimentally verified. But what if time itself could be manipulated, bent, or even reversed? This idea opens up a Pandora's box of possibilities, inviting questions about how we might traverse the vast corridors of time. Another fascinating theory that has captured the imaginations of both scientists and science fiction enthusiasts is the concept of wormholes. These hypothetical passages through the fabric of spacetime could, in theory, connect two distant points in the universe. Imagine a tunnel with two openings, each located in different parts of the cosmos, or, more intriguingly, in different times. While we have yet to confirm the existence of such structures, the mathematics of general relativity suggests they could exist. If wormholes could be stabilized and traversed, they might allow for instantaneous travel across unimaginable distances, or perhaps even backward through time. Picture traveling from one star system to another in the blink of an eye. The thought alone is revolutionary. Yet the challenges are immense. The very stability of a wormhole remains one of the most significant hurdles. Any disruption to this delicate structure could cause it to collapse with potentially catastrophic consequences. As if the theory of wormholes were not mind-bending enough, quantum mechanics introduces yet another layer of complexity to our understanding of time. The many worlds interpretation of quantum mechanics proposes that every decision, every action, leads to the creation of a new, branching universe. This branching, in turn, gives rise to a vast multiverse of possibilities. If time travel were possible, this raises the tantalizing question, what happens if one were to change a significant event in the past? Could this alter reality so profoundly that it creates an entirely new timeline, separate from the original? The prospect of interacting with alternate realities brings with it a host of paradoxes, the most famous being the grandfather paradox. This paradox questions the very nature of time travel. If one were to go back and change something as significant as the death of their own grandfather, would that prevent their own existence? Would it unravel the very fabric of their reality? Philosophically speaking, time travel takes us to the very heart of some of the most profound questions about existence. If we were able to travel through time, how would we reconcile the relationship between cause and effect? What would become of free will in a world where time is not a fixed linear progression? These questions touch on deep metaphysical issues that have occupied the minds of thinkers for centuries. Time, in its mysterious and mutable nature, raises not only scientific inquiries but also existential ones. Could our perception of time be a mere illusion, a construct of our limited understanding? The ongoing research into time travel continues to challenge and expand our conception of the universe, urging us to rethink the very nature of reality itself. Perhaps one of the most intriguing possibilities lies in the potential application of wormholes to interstellar travel. If these theoretical passages could be stabilized and made accessible, they would revolutionize the way we think about space exploration. Instead of sending spacecraft on long, arduous journeys across vast interstellar distances, a wormhole might provide a shortcut, allowing ships to bypass the barriers of space itself. Imagine this: a spacecraft entering a wormhole at one end, emerging almost instantaneously at the other end, light years away. It's a concept that stretches the boundaries of our imagination. General relativity, which describes how gravity warps the fabric of space-time, provides the theoretical foundation for such phenomena. The equations suggest that if a stable wormhole could be created, it could shrink the distance between two distant points, reducing travel time from years to mere moments. But before we get carried away with these possibilities, we must confront the monumental challenges of creating or discovering a stable wormhole. The technology and materials required are at this point beyond our reach. Exotic matter, a hypothetical substance that would be required to stabilize a wormhole, has yet to be discovered. And even if such matter were found, there's no guarantee that a wormhole could be maintained for long enough to make interstellar travel viable. Any disturbance to the structure of the wormhole could cause it to collapse, trapping anyone inside and potentially leading to catastrophic outcomes. The future of wormholes, like time travel itself, is firmly rooted in the realm of theoretical speculation. Yet, the very study of wormholes has sparked a wave of innovative thinking, driving researchers to explore new frontiers in physics and cosmology. If we one day unlock the mysteries of wormholes and time travel, the horizon of human exploration could be dramatically expanded. The distant stars, which have long been out of our reach, could suddenly seem within our grasp. Space itself could become navigable in ways we never thought possible, changing the future of humanity in ways that are difficult to predict. As we continue to gaze into the stars, we might find that the future of space exploration lies not in conventional spacecraft, but in the uncharted realms of theoretical physics. In the search for answers, the holographic principle represents a compelling and deeply philosophical idea in theoretical physics. This principle suggests that our three-dimensional universe, the world we perceive with our senses, may be nothing more than an illusion, a hologram, so to speak. The idea arose from the study of black holes and quantum gravity, as scientists attempted to understand how information is encoded in these enigmatic objects. It was discovered that all the information contained within a black hole might not be stored in its three-dimensional volume, but instead on its two-dimensional surface. This revelation led to the groundbreaking suggestion that our entire universe, every galaxy, every star, every particle, could be a projection of information encoded on a lower dimensional boundary. One of the most intriguing implications of this principle is its potential to bridge the gap between two of the most fundamental forces in the universe: gravity and quantum mechanics. Gravity, which governs the behavior of massive objects like stars and galaxies, and quantum mechanics, which dictates the behavior of particles on the smallest scales, have long been considered incompatible. The holographic principle, however, suggests that these two forces might be more closely connected than we realize. It hints at the possibility that our perception of three-dimensional space could be a manifestation of deeper, more fundamental, two-dimensional information. This idea challenges everything we think we know about reality, suggesting that the universe as we experience it may be just a projection of something far more profound. The holographic principle, though still in the realm of theory, has profound implications for our understanding of the cosmos and our place within it. The holographic principle, a concept that has shaken the foundations of our understanding of reality, raises profound and far-reaching questions about the very nature of existence. Imagine if all the information about everything that happens in our universe could be traced back to a lower dimensional source, a kind of cosmic blueprint. Such an idea challenges everything we think we know about dimensions and the structure of reality itself. If this principle holds true, then what we perceive as depth, solidity, and the very fabric of space and time may not be fundamental at all. Instead, they could be emergent phenomena arising from something more basic, a universe built on layers of information far more intricate than we could ever imagine. This notion isn't just the subject of abstract theorizing, but the focus of serious exploration by physicists and philosophers alike. The holographic principle opens up tantalizing avenues of inquiry, prompting us to reconsider how time, space, and consciousness interact within the cosmos. As researchers probe deeper into its implications, one thing becomes increasingly clear. Understanding this principle may offer the key to unifying the vast array of forces that shape our universe, from the microscopic realm of quantum particles to the grand scale of black holes and beyond. But the holographic principle is far from being the only idea challenging our notions of reality. The concept of parallel universes, or the multiverse, introduces a further layer of complexity, one that could radically transform our perceptions of existence. What if our universe is not the only one? What if, in fact, there are countless others, each with its own unique set of physical laws, constants, and histories? This mind-bending idea suggests that there could be an infinite number of parallel universes, each one slightly or vastly different from our own. Imagine a universe where every choice, no matter how small, leads to a new reality. Perhaps in one universe, a different decision at a key moment in history completely altered the course of events. In another, the opposite choice led to an entirely different outcome. This idea that every possible decision spawns its own universe is both awe-inspiring and humbling. The implications are staggering. It means that the reality we experience is but one thread in a vast, branching web of possibilities. In this framework, the idea of fate takes on a new meaning, as it becomes intertwined with choice and consequence in ways we are only beginning to understand. Such ideas aren't just speculative fiction. They emerge from the heart of quantum mechanics, where the many worlds interpretation proposes that every quantum event, every moment when a particle can behave in multiple ways, actually results in a split, giving birth to new universes. In this view, every outcome occurs, creating parallel realities that stretch our understanding of time, space, and the fundamental nature of the universe. These ideas are profoundly challenging, pushing the boundaries of both science and philosophy as they raise difficult questions about the nature of time and reality itself. Yet, even with all the theoretical elegance, these ideas present a daunting challenge. How do we test the existence of these parallel universes? The inability to observe them directly leaves scientists grappling with a frustrating paradox. Nevertheless, this doesn't deter researchers. Rather, it drives them to develop new ways of thinking and new tools for probing the nature of reality. The search for evidence of the multiverse, or for ways to connect with these alternate realms, remains one of the most exciting and elusive pursuits in modern physics. Similarly, the concept of a cyclic universe offers another mind-expanding possibility. Instead of the universe having a singular beginning with the Big Bang and a definitive end, some theorists propose that the cosmos goes through endless cycles of expansion and contraction. This idea has gained traction in recent years, fueled by fascinating discoveries in cosmology. For instance, the cosmic microwave background radiation, the faint afterglow of the Big Bang, contains subtle patterns that might suggest the universe has undergone previous cycles, epochs of expansion and contraction that stretch back far beyond the origins of our current cosmos. Such evidence is further supported by the behavior of galaxies. Over vast periods of time, galaxies and clusters of galaxies have appeared to evolve in ways that suggest a dynamic, cyclical process, rather than a simple, linear progression. Galaxies don't just form and grow. They collide, merge, and transform, suggesting that these processes could be influenced by previous cosmic cycles, each one leaving a mark on the universe we see today. Theories based on string theory and quantum gravity add further intrigue to the idea of a cyclic universe. They propose that the forces governing the universe could allow for cycles of expansion and contraction, predicting that the universe could bounce back from a contracting phase, giving rise to an infinite series of cosmic births and rebirths. While these theories remain speculative, they offer an attractive narrative that aligns with many of the strange observations we've made about the universe's past and present. The idea that our universe might be part of an eternal series of transformations rather than a one-off creation is both humbling and profound. Yet, even as we entertain the possibility of a cyclic universe, another pressing question arises. What is the fate of our current universe? Observations suggest that the universe is expanding at an ever-accelerating rate. Some scientists believe this could lead to a scenario known as the Big Freeze, in which galaxies drift further apart, stars burn out, and the universe grows cold and dark. However, other models suggest that gravity could eventually overcome the universe's expansion, pulling everything back together in a contraction phase, eventually leading to another Big Bang. This interplay of forces, the expansion and contraction of space itself, remains one of the most intriguing mysteries in cosmology, suggesting that the universe's true nature may be far more complex and cyclical than we can currently grasp. Finally, quantum entanglement offers another striking challenge to our understanding of reality, especially when it comes to distance and communication. In the world of quantum mechanics, particles can become entangled, meaning that their states are intrinsically linked, regardless of the distance between them. If one particle changes, the other changes instantaneously, no matter how far apart they are. This violates our everyday understanding of communication, which is always constrained by the speed of light. Classical physics tells us that information must travel through space and takes time to do so. But quantum entanglement suggests that, on a fundamental level, this isn't always the case. One of the most famous experiments that illustrates the strange nature of entanglement is Bell's theorem. This theorem shows that if local realism, essentially the idea that objects have definite properties independent of observation, holds true, then the measurements of entangled particles should correlate in a way that classical physics would predict. However, experiments have consistently shown that entangled particles behave in ways that defy classical expectations, leading to a profound realization. The universe may not operate in the way we think it does, and our understanding of space, time, and reality itself could be fundamentally flawed. In each of these areas, holography, parallel universes, the cyclic nature of the cosmos, and quantum entanglement, we find ourselves grappling with the limits of our knowledge. Each breakthrough, each new theory, brings us closer to understanding the true nature of the universe, but it also opens up more questions, more mysteries to explore. The journey of discovery is far from over, and as we continue to push the boundaries of science and philosophy, we are constantly reminded of just how much we have yet to learn about the universe and about ourselves. Experiments consistently yield results that align closely with quantum mechanics, providing powerful evidence of phenomena that seem to defy our classical understanding. The most striking of these is the phenomenon of quantum entanglement, a strange and mysterious effect where particles, regardless of how far apart they are, seem to communicate instantaneously, their states deeply intertwined. This uncanny correlation cannot be explained without accepting the inherently non-local nature of entanglement, which challenges the very foundations of space and time as we know them. What's more, the implications of entanglement reach far beyond mere communication. They hint at a far deeper, more interconnected fabric of reality, where everything is subtly linked. This defiance of classical interpretations of physics not only continues to fascinate scientists, but it also opens the door to practical, transformative applications. Quantum entanglement is at the heart of revolutionary fields such as quantum computing and cryptography, where the unique properties of entangled particles hold the key to breakthroughs in information processing and secure communication. As our understanding of entanglement evolves, so too does the potential to redefine the limits of human connection and knowledge, particularly in a world where distance is no longer a barrier to the exchange of information. Meanwhile, on the grander scale of the universe, a force known as dark energy is playing a fundamental role in its expansion. Since the late 20th century, astronomical observations have revealed an astonishing discovery. The universe is not merely expanding, but the expansion is accelerating. This increase in speed can be attributed to dark energy, an enigmatic force that seems to counteract the gravitational pull of matter, driving galaxies apart at an ever-increasing rate. One way to conceptualize the influence of dark energy is to imagine it as a form of negative pressure within the very fabric of space itself. As the universe stretches outward, more space is created between galaxies, and dark energy pushes this expansion forward, unlike gravity, which pulls matter together. This leads to a growing separation between galaxies over time, a phenomenon that challenges our prior understanding of the universe's fate and suggests a future where expansion continues indefinitely. Current scientific models estimate that dark energy comprises approximately 70% of the total energy density of the universe, making it a dominant yet elusive force. One of the leading theories, the cosmological constant, proposes that dark energy remains constant throughout the universe's lifespan. However, other theories suggest that dark energy may evolve, influencing the expansion in varying ways. These competing ideas reflect the complexity of unraveling the true nature of dark energy, which, despite its mysterious qualities, clearly influences the structure of the cosmos. Evidence of dark energy's impact can be seen in cosmic microwave background radiation and the way galaxies are distributed across the universe. As scientists continue their research, the true nature of dark energy may eventually reveal much more about the fate of the universe and our place within it. The question of the universe's ultimate fate has long been a subject of intrigue among scientists and philosophers. Several theories have emerged, each suggesting a different potential outcome. One of the most widely discussed scenarios is the Big Freeze. This hypothesis envisions a future where the universe continues to expand, galaxies drift further apart, and stars burn out, eventually exhausting their nuclear fuel. The result would be a cold, dark, and empty cosmos, with only scattered remnants of celestial bodies lingering in a lifeless expanse. Alternatively, the Big Crunch proposes a more dramatic fate. This theory suggests that the expansion of the universe could eventually halt and reverse, pulled back by the force of gravity. In this scenario, galaxies would draw closer together, ultimately colliding and merging, possibly leading to the universe collapsing into a singularity, a point of infinite density. This return to a state similar to the universe's origin raises fascinating questions about cosmic cycles and the possibility of rebirth. A third theory, the Big Rip, imagines a far more violent end. According to this idea, dark energy's influence could grow stronger over time, accelerating the universe's expansion to the point where galaxies, stars, and even atoms themselves are torn apart. In this chilling vision, the universe literally falls apart at the seams, with each layer of matter succumbing to the increasingly intense forces pulling everything apart. These theories not only provoke profound philosophical reflections on the nature of existence, but also challenge our fundamental understanding of time, space, and the forces that shape the cosmos. As scientists continue to explore the mysteries of the universe, the true fate of our vast home remains one of the most enduring and profound questions in modern science. Each hypothesis offers valuable insights into the very structure of reality, but none can yet claim to hold the final answer. Looking back through history, it is evident that humanity's fascination with the stars is not a modern pursuit. Ancient civilizations, though separated by millennia and continents, demonstrated a remarkable understanding of astronomy, evident in their architecture and technologies. For example, the ancient Egyptians built the Great Pyramids of Giza with such precision that their alignment with the cardinal points of the compass is almost flawless. This precision was not coincidental. It was based on meticulous observations of the stars, which informed the placement of these monumental structures. The alignment underscores the Egyptians' advanced understanding of celestial movements and their significance in both practical and spiritual terms. Similarly, the ancient Mayans crafted an incredibly accurate calendar system based on the cycles of the sun, moon, and planets. This calendar not only tracked time, but also predicted astronomical events, such as eclipses, with astonishing precision. The Mayans built massive observatories like those at Uaxactun and Chichen Itza, where they could observe the heavens and track the movements of celestial bodies with remarkable accuracy. In Greece, one of the most remarkable artifacts from the ancient world is the Antikythera mechanism, an ancient analog computer discovered in a shipwreck off the coast of Antikythera. Designed to predict astronomical positions and eclipses, this sophisticated device demonstrates the ancient Greeks' profound understanding of celestial mechanics and engineering. The intricate gears and design of the Antikythera mechanism reveal a level of technological innovation that was previously thought to be unattainable for ancient civilizations. Another example of ancient astronomical knowledge is found in the megalithic structures of Stonehenge in England. Built over 5,000 years ago, Stonehenge's stones are precisely aligned with the summer solstice and lunar cycles, reflecting the builders' deep knowledge of the stars and their ability to track time. The placement of these stones suggests that the people who constructed Stonehenge not only understood the movements of celestial bodies, but may have also used the site for rituals and ceremonies tied to the heavens. These examples serve as a powerful reminder that advanced knowledge of the cosmos was not the exclusive domain of modern science, but was deeply embedded in the cultures of ancient civilizations. Their achievements continue to awe and inspire, offering us a glimpse into the deep connection humanity has had with the stars for millennia. In the modern era, scientists utilize advanced tools like radio telescopes to peer into the far reaches of the universe. Unlike optical telescopes, which detect visible light, radio telescopes capture radio waves emitted by celestial objects. These radio waves, invisible to the naked eye, carry valuable information about a wide array of cosmic phenomena, including pulsars, quasars, and even the cosmic microwave background radiation, remnants from the universe's earliest moments. When a radio wave reaches Earth, it is collected by the large dish of the radio telescope, where it is amplified and translated into data. Scientists can then analyze the frequency, intensity, and timing of these waves to unravel clues about the structure and behavior of the universe. The study of pulsar signals, for example, has provided important insights into the nature of gravity and the fabric of space-time itself. In this way, radio telescopes allow us to explore the universe in a way that visible light alone cannot, providing us with a new lens through which to understand the cosmos. Radio telescopes have proven to be one of the most captivating and essential tools in the search for extraterrestrial intelligence. These sophisticated instruments are tirelessly scanning the heavens, listening for signals that stand out from the natural cosmic background, which is often noisy and overwhelming. Scientists are not just using traditional observational techniques, but also harnessing the power of advanced algorithms and machine learning to sift through vast oceans of data. In this search, subtle anomalies are sought that could be indicative of something extraordinary, potential signs of intelligent life from distant stars. One of the most intriguing and famous examples of this phenomenon is the mysterious WOW signal, recorded in 1977. The signal, which remains unexplained to this day, sparked widespread curiosity and spurred further investigations. The possibility that this signal was of extraterrestrial origin still lingers in the minds of researchers, even after decades of exploration. Radio telescopes are uniquely powerful because they can operate across an extensive range of frequencies, allowing them to penetrate cosmic dust clouds and gases that often obscure traditional optical observations. This multi-frequency approach to cosmic exploration provides a unique vantage point for understanding the universe, helping scientists to peer through the veil of interstellar dust and uncover the secrets of faraway worlds. By observing the universe in this way, radio telescopes are expanding our understanding of the cosmos and shedding light on its origins and evolution. Looking toward the future, the capabilities of radio telescopes continue to evolve. As science advances, so too does the potential for these instruments to break new ground in our quest to understand the universe. Beyond the search for extraterrestrial intelligence, radio telescopes may soon play a key role in probing other mysterious and exciting realms of cosmic exploration, such as the subsurface oceans on icy moons like Europa and Enceladus. The quest to explore these subsurface oceans has become a focal point in the search for extraterrestrial life and in understanding the dynamics of our solar system. Advancements in technology are enabling scientists to develop new tools for accessing these frozen worlds. One promising technology is the use of autonomous underwater vehicles, AUVs. These robots are designed to navigate the frigid dark waters beneath thick layers of ice. Equipped with an array of sensors, they can collect crucial data about temperature, salinity, and chemical composition in these alien oceans. In addition to AUVs, ice-penetrating radar systems are being developed to map the thickness of the ice that covers moons like Europa and Enceladus. These radar instruments, which can be deployed from orbit, will allow scientists to identify regions where the ice may be thin enough to access the subsurface oceans below. This information will be invaluable in selecting landing sites for future missions, as well as designing landers and drills capable of reaching these alien waters. A key challenge in exploring these icy moons is developing specialized drill technologies that can melt through thick layers of ice without contaminating the pristine ecosystems beneath. New drilling systems, some of which use small nuclear or thermal heating elements, are being designed to make these explorations possible. These drills will create openings in the ice, allowing researchers to access the oceans below while minimizing contamination from Earth. Maintaining the integrity of these ecosystems is essential to ensure valid scientific measurements and avoid the introduction of terrestrial contaminants that could jeopardize the search for life. At the same time, scientists are equipping orbiters with advanced spectrometers that can analyze the surface of moons like Europa and Enceladus for signs of water vapor and other chemical indicators of subsurface oceans. By studying the plumes of material ejected from Enceladus and the surface features of Europa, mission planners can gather crucial clues about what lies beneath the surface. These technological innovations represent a bold new era in our exploration of the outer solar system and bring us closer to answering the question of whether these hidden alien oceans could harbor life. The search for extraterrestrial intelligence, or SETI, has long captivated the imagination of scientists and the public alike. At the forefront of this search is a highly sophisticated array of technologies designed to detect signals from distant civilizations. Radio telescopes, such as the ones at the Arecibo Observatory before its collapse, and the Green Bank Telescope are key tools in this endeavor. These powerful instruments are capable of capturing a vast range of radio frequencies, offering scientists an unparalleled ability to listen to the cosmos. The reason that SETI focuses so heavily on radio waves is rooted in the belief that any advanced civilization would likely use electromagnetic waves to communicate, as much as we do here on Earth. By scanning the skies for unusual or unexplained signals, SETI aims to uncover any hints that might point to intelligent life beyond our planet. These signals could come in many forms, but the task of detecting them is not straightforward. With so much natural cosmic noise surrounding us, distinguishing a genuine signal from the overwhelming background is no easy feat. Advancements in technology have provided a significant boost to SETI's efforts, particularly in the realm of data analysis. The amount of data gathered by radio telescopes is staggering, sometimes reaching hundreds of terabytes each day. To handle this data, scientists rely on cutting-edge software, including artificial intelligence and machine learning algorithms, to filter out unwanted signals, such as those from Earth-based satellites and aircraft. This helps narrow the focus to more promising candidates that might contain signals of extraterrestrial origin. Machine learning in particular has become indispensable in this process. As algorithms are exposed to more data, they improve over time, becoming more adept at recognizing patterns and identifying potential extraterrestrial signals. This technology is constantly evolving, allowing scientists to sift through data more efficiently and to spot subtle anomalies that could be missed by human researchers. Moreover, SETI has embraced innovative approaches like crowdsourcing through projects such as SETI at Home. This initiative allows volunteers from around the world to contribute their personal computing power to the search for extraterrestrial signals. By leveraging the computational power of thousands of volunteers, SETI is able to analyze far more data than any single organization could manage. This global network of citizen scientists is helping to expand the search for life in the universe, providing a unique and collaborative way to involve the public in scientific discovery. As artificial intelligence continues to develop, its potential to revolutionize our understanding of the cosmos is immense. AI's ability to process data at incredible speeds opens up new possibilities for discovering celestial phenomena. For example, in the search for exoplanets, machine learning algorithms are able to analyze the light curves of distant stars, detecting small, subtle dips in brightness that indicate a planet may be passing in front of its star. These AI systems have already played a crucial role in identifying thousands of exoplanets across our galaxy. The rapid development of these technologies continues to expand our understanding of the universe and may one day help us answer one of humanity's oldest questions: are we alone in the cosmos? In this exciting era of cosmic exploration, the blending of artificial intelligence, machine learning, and advanced technologies such as radio telescopes, autonomous underwater vehicles, and ice-penetrating radar is propelling us closer to uncovering the secrets of our universe. Whether through the search for extraterrestrial intelligence or the study of distant moons, these technologies are opening new frontiers in our understanding of the cosmos and our place within it. Each breakthrough brings us one step closer to answering the profound questions that have fascinated humanity for centuries. What lies beyond our world, and are we truly alone in the vastness of space? Artificial intelligence, AI, is becoming an indispensable tool in the quest to understand the most elusive and dramatic phenomena in the universe, particularly when it comes to gravitational waves. These ripples in the fabric of space-time, which are created by events such as the merging of black holes, have the potential to reveal secrets of the universe's most violent processes. However, detecting these subtle signals in the midst of overwhelming noise from observational data is no small task. Here, AI steps in with advanced algorithms designed to sift through vast quantities of data, isolating the faint echoes of cosmic events. By doing so, AI not only helps scientists detect these ripples, but also assists in analyzing their properties, shedding light on the underlying mechanics of these powerful phenomena. In doing so, it opens a window into understanding the most dramatic processes shaping our universe. But AI's role does not stop at data analysis. It extends to the design of new experiments and instruments as well. By simulating various cosmic scenarios, AI can suggest ways to optimize observational strategies. This ensures that telescopes and instruments are focused on the most promising targets, enabling astronomers to direct their resources more effectively. The synergy between human creativity and machine learning is proving to be a dynamic force in the field of cosmology, propelling the exploration of the universe into new realms of discovery and understanding. The potential for collaboration between human ingenuity and AI is pushing the boundaries of what we know, enabling us to delve deeper into the cosmos than ever before. In parallel to these advancements in artificial intelligence, robotic missions have revolutionized our ability to explore and understand our solar system. These incredible machines, designed to withstand the harshest conditions of space, act as our eyes and ears in the vast expanse beyond Earth. Robotic spacecraft are capable of traveling to distant planets, moons, and asteroids, collecting data that would otherwise be impossible for humans to acquire in person. Their technology continues to evolve, allowing them to gather invaluable information about the origins and dynamics of our solar system. Take, for example, the Voyager spacecraft, which was launched in the late 1970s. Voyager has traveled farther than any other human-made object, sending back a steady stream of data about the outer planets and the interstellar medium. Its journey has fundamentally reshaped our understanding of planetary atmospheres, magnetic fields, and the nature of space itself. Similarly, missions like the Mars rovers have unearthed crucial evidence of past water flows, hinting that Mars may have once had conditions suitable for life. Robots like the Juno spacecraft, which is currently orbiting Jupiter, are conducting in-depth studies of the gas giant's composition and magnetosphere, further expanding our understanding of these colossal celestial bodies. Each mission, whether focused on planetary exploration or the study of distant moons, plays a vital role in piecing together the puzzle of our solar system's formation and evolution. This data is invaluable, as it offers insight not only into our solar system, but into the broader processes that govern planetary formation across the cosmos. As robotic missions continue to venture into uncharted territory, such as New Horizons' flyby of Pluto and its subsequent journey into the Kuiper Belt, we gain access to unprecedented knowledge about the outer realms of our solar system. The wealth of information these robotic explorers are collecting enables researchers to refine their models of celestial phenomena, unlocking secrets of the universe that were previously out of reach. Through these missions, humanity is gaining a clearer and more comprehensive understanding of its place in the universe. In tandem with these advancements in space exploration, recent breakthroughs in space-time mapping have been driven by a combination of theoretical physics and cutting-edge technology. Researchers have developed increasingly sophisticated models that describe the curvature of space-time, which is influenced by the presence of massive objects like stars and black holes. Instruments like laser interferometers, which are designed to detect gravitational waves, allow scientists to observe the ripples caused by energetic cosmic events. These gravitational waves, first detected in 2015, provide invaluable clues about the most violent and energetic events in the universe, shedding light on the very fabric of space-time itself. Another breakthrough comes in the form of advanced imaging techniques, which have allowed astronomers to capture high-resolution images of phenomena on a cosmic scale. Radio telescopes and arrays that span vast distances on Earth are enabling us to peer into the far reaches of the universe, capturing images that reveal the inner workings of black holes and other extreme cosmic objects. One of the most significant achievements in this area was the Event Horizon Telescope's groundbreaking image of the black hole at the center of the Milky Way galaxy. This image has provided researchers with new insights into the behavior of gravity around supermassive black holes, allowing them to refine their models of spacetime and black hole dynamics. While these advancements in spacetime mapping and observational techniques are providing us with clearer images and deeper understanding, significant challenges remain. One of the most profound mysteries still facing scientists is how to reconcile general relativity, which governs the behavior of massive objects and large-scale cosmic phenomena, with quantum mechanics, which operates at the microscopic level. This search for a unified theory, one that can bridge the gap between these two foundational pillars of physics, continues to elude physicists and is one of the most tantalizing intellectual pursuits in modern science. Another key mystery is the nature of dark matter and dark energy. These two invisible components make up approximately 95% of the universe's mass and energy, yet their properties remain poorly understood. Despite their elusive nature, dark matter and dark energy have significant effects on space-time, influencing the behavior of galaxies and the structure of the universe. Understanding them is one of the most urgent tasks in modern cosmology. The concept of causality and how it relates to space-time also raises intriguing questions. If space-time can be warped by extreme gravitational forces, what are the implications for travel and communication across vast distances? Could such warping allow for shortcuts in space or even time travel? These questions challenge us to reconsider our basic assumptions about the nature of reality, and the answers may have profound implications for how we understand the universe. One particularly captivating phenomenon that has garnered significant attention is gravitational lensing. This occurs when massive objects like galaxies or clusters of galaxies bend the light from distant sources due to their immense gravitational pull. As light passes near these massive objects, its path is distorted, and astronomers can observe this bending effect as arcs or multiple images. This phenomenon provides an invaluable tool for studying dark matter, an elusive substance that, while invisible, exerts a gravitational influence on the universe. By studying the distortions caused by gravitational lensing, scientists can infer the amount and distribution of dark matter in a given system, helping to map out its role in the structure of the universe. One of the most astonishing discoveries made through gravitational lensing is that dark matter does not cluster in the same way as visible matter. Instead, it forms a diffuse halo around galaxies, influencing their motion and the formation of larger cosmic structures. This finding challenges our previous understanding of galaxy formation, suggesting that dark matter plays a far more complex and integral role in shaping the cosmos than previously thought. This revelation is just one example of how gravitational lensing is helping us understand the mysterious and largely invisible forces that govern the universe, and how the interplay between dark matter and visible matter shapes the universe's evolution. In the grand scheme, these ongoing discoveries and technological advancements are providing us with a deeper understanding of the forces that govern the universe. while simultaneously revealing how much there still is to learn. The mysteries of space-time, dark matter, and cosmic events continue to challenge humanity's intellectual boundaries, inspiring us to look further into the unknown and to explore the vast and intricate workings of the cosmos. Gravitational lensing, one of the most fascinating phenomena in astrophysics, has propelled our understanding of the universe to new frontiers. Through this process, the immense gravity of objects like galaxy clusters bends and distorts the light from more distant celestial bodies. This bending acts like a cosmic magnifying glass, unveiling previously hidden structures that otherwise might never have been detected. In particular, when scientists studied the lensing effects of galaxy clusters, they uncovered previously unseen members of these clusters, offering a deeper look at their true size and composition. More significantly, this revelation illuminated the pervasive influence of dark matter, an elusive substance that makes up the majority of the universe's mass, but remains invisible to conventional observation. These findings have prompted some researchers to propose that future surveys of gravitational lensing could provide the key to understanding dark matter's nature, unlocking new realms of physics that could drastically reshape our view of the cosmos. With each new lensing event, the cosmic enigma of dark matter grows a little clearer, one distorted image at a time. Simultaneously, simulations play a pivotal role in refining our understanding of the universe's infancy. These complex virtual laboratories enable scientists to recreate the conditions that existed shortly after the Big Bang. By simulating these early moments, when the universe emerged from an extraordinarily hot and dense state, researchers can model the interactions of mass and energy that shape the universe's evolution. This allows for the examination of how galaxies and galaxy clusters might have formed from the primordial plasma driven by gravitational forces. These simulations are invaluable for investigating how matter clumped together in the chaotic early universe to form the cosmic structures we see today. By comparing the outcomes of simulations with real-world observations from telescopes, scientists can validate their theories about how the universe expanded and evolved, refining their understanding of its grand narrative. Another vital tool in these simulations is the study of the cosmic microwave background radiation, often considered the faint afterglow of the Big Bang. This radiation holds critical clues about the universe's early conditions. The subtle temperature fluctuations within the cosmic microwave background reveal vital details about the density and distribution of matter shortly after the Big Bang. Simulations are essential for understanding how these fluctuations, or anisotropies, came to be, providing scientists with insights into the universe's rate of expansion and the conditions that prevailed at its birth. Beyond these early moments, simulations also help explore the implications of theories like cosmic inflation, an idea that suggests the universe expanded at an extraordinary rate in its earliest fractions of a second. By adjusting their models to account for different inflationary scenarios, researchers can predict how these conditions might have led to the observable universe we now study. The search for new knowledge has also propelled scientists to explore the mysteries of particle physics, with particle accelerators serving as powerful tools to probe the fundamental forces and particles that govern the universe. Among the most significant discoveries was the detection of the Higgs boson in 2012 at the Large Hadron Collider, a breakthrough that confirmed the last missing piece of the standard model of particle physics. The Higgs boson explained how particles acquire mass, ultimately shaping the structure of the universe itself. Yet the role of particle accelerators extends far beyond this singular discovery. By recreating the extreme conditions present just moments after the Big Bang, these accelerators allow researchers to observe the behavior of quarks and gluons, the fundamental constituents of protons and neutrons. This high-energy environment gives scientists insight into how matter behaves under the most extreme conditions, such as those that might have existed in the universe's earliest moments. Moreover, particle accelerators open a window into some of the universe's greatest unresolved mysteries, such as dark matter and antimatter. These enigmatic substances remain largely invisible and elusive, but particle collisions at near light speeds can offer clues that might bring us closer to understanding their properties. Another key area of interest for particle physicists is supersymmetry, a theoretical framework suggesting that every particle we know has a partner particle. Though unproven, this theory could provide solutions to many lingering questions in physics, such as the nature of dark matter and the unification of fundamental forces. The pursuit of these ideas drives experiments that stretch the boundaries of current scientific knowledge, often revealing strange phenomena that challenge existing models and spark further investigation. Beyond their contributions to fundamental physics, the technologies developed within the realm of particle accelerators have proven invaluable in other fields. For example, the advancements in particle detection techniques have been adapted for medical purposes, such as improving cancer treatments and revolutionizing medical imaging. The ability to observe and manipulate particles with such precision has led to breakthroughs that extend well beyond the accelerator, demonstrating how the study of the smallest scales of matter can have profound effects on the larger world. In this way, the quest to understand the universe at its most fundamental level continues to have tangible benefits for life on Earth. Mars, our neighboring planet, has been a focal point of scientific curiosity, particularly in the search for evidence of past life. The discovery of ancient water, essential for life as we know it, has fueled this interest. In recent years, rovers such as Curiosity and Perseverance have provided compelling evidence that liquid water once flowed across the Martian surface. River deltas, lake beds, and mineral deposits suggest that Mars was once a much more hospitable place capable of sustaining life. These geological features imply that water didn't merely exist but was also chemically active, creating conditions that could have supported microorganisms. In addition to water, scientists have uncovered carbonates and sulfates embedded in Martian rocks. These minerals are often associated with biological processes on Earth, further suggesting that Mars may have once hosted life. The presence of these minerals doesn't just indicate that water was once abundant, it points to a more complex environment, one that could have harbored life in some form. While we haven't yet found definitive proof of Martian life, the evidence we've gathered paints a tantalizing picture of a world where life might have once taken root. With each discovery, we come closer to answering one of humanity's most profound questions. Are we alone in the universe? Furthermore, a growing body of research surrounding Martian meteorites found on Earth has uncovered a tantalizing discovery: the presence of organic molecules, the very building blocks of life. These molecules raise profound questions about the potential for ancient microorganisms to have once existed on Mars. In more recent missions, scientists have detected methane in Mars's atmosphere, a gas that, while it can arise from geological processes, is commonly produced by living organisms on Earth. The presence of methane, along with its fluctuating cycles, suggests the possibility of ongoing processes, whether biological or geological, that merit further scrutiny. Each new piece of evidence builds upon the last, adding depth to the growing narrative that Mars may have once hosted microbial life. With every rover mission and analytical study, we edge closer to answering the age-old question of whether life ever existed beyond Earth. These discoveries fuel a sense of curiosity that pushes humanity's exploration of the cosmos forward. The drive to understand the potential for life elsewhere continues to inspire research, technology, and the collective imagination of our species. Mars is just the beginning. The exploration of exoplanets, planets beyond our solar system, presents another frontier in the quest to determine whether life exists elsewhere in the universe. To study these distant worlds, scientists combine astronomy, planetary science, and even biology in a complex, multifaceted approach. One of the key factors in this search is the planet's location within the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where conditions are ideal for liquid water to exist, neither too hot nor too cold. If a planet resides too close to its star, it may be scorched beyond all possibility of supporting life. Conversely, if it is too distant, it could be frozen over, offering no potential for life as we know it. But distance alone doesn't determine habitability. The composition of a planet's atmosphere plays a crucial role as well. An atmosphere can serve as a protective shield, deflecting harmful radiation from space and regulating temperature to create stable conditions. To investigate these planetary atmospheres, scientists use a technique called spectroscopy. By analyzing the light spectrum that passes through a planet's atmosphere, they can identify the presence of gases such as oxygen, carbon dioxide, and methane, molecules that may hint at biological processes. In addition to atmospheric analysis, the planet's composition and geological activity are critical factors. Rocky planets with solid surfaces are far more likely to support life than gaseous giants. Furthermore, the presence of minerals, volcanic activity, and a stable climate are all necessary conditions for life. The existence of a magnetic field, which shields a planet from solar radiation, is also an important factor in determining whether life can thrive on a planet. While the study of exoplanets is still in its early stages, technological advancements are accelerating our understanding. With each new discovery, scientists get one step closer to comprehending not only where life could exist, but also the unique conditions that could support it. These advances also inform the search for life on planets within our own solar system, deepening our understanding of the potential for life beyond Earth. In this quest, Extremophiles, organisms that survive and thrive in Earth's most hostile environments, serve as a key piece of the puzzle. These remarkable creatures endure extreme temperatures, intense radiation, high acidity or alkalinity, and crushing pressures, conditions that would be lethal to most forms of life. Their existence demonstrates the extraordinary adaptability of life, suggesting that life could persist in environments previously thought to be uninhabitable. Microorganisms living in deep ocean vents, for instance, use chemosynthesis rather than photosynthesis, deriving energy from chemical reactions instead of sunlight. This remarkable ability to adapt to extreme conditions opens up the possibility that similar processes could support life on other planets, where sunlight is absent but chemical energy is abundant. The study of extremophiles has profound implications for astrobiology, the study of life in the universe. By examining these resilient organisms, scientists can develop methods to search for life on other worlds. For example, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, may harbor subsurface oceans that could resemble the extreme environments where extremophiles thrive on Earth. These moons, with their hidden water reservoirs and potential for geothermal activity, represent some of the most promising targets in the search for extraterrestrial life. The concept of extremophiles expands our imagination and redefines the limits of life's potential. Their resilience in the face of harsh conditions encourages scientists to push the boundaries of exploration, inspiring missions to the farthest reaches of space. If life can exist in Earth's most extreme environments, it stands to reason that life could also survive, and perhaps even thrive, on distant worlds. Europa, one of Jupiter's largest moons, offers one such exciting possibility. Beneath its icy surface lies a vast ocean of liquid water, believed to be in contact with a rocky seabed. This interaction could provide a rich, stable environment similar to the deep-sea hydrothermal vents on Earth, where unique ecosystems flourish in total darkness, powered by chemical energy. Liquid water, essential for all known forms of life, may be present in the oceans of Europa, kept warm by tidal heating, a process caused by the gravitational interactions between Jupiter and its moons. This natural heating mechanism prevents the ocean from freezing solid, creating a stable environment that could potentially support life. As we continue to explore the cosmos, the search for life on Europa and other distant worlds challenges our understanding of what is necessary for life to exist. It encourages us to think beyond the Earth-centric view of life and to consider the possibilities in environments that we might once have considered too extreme. Whether on Mars, Europa, or an exoplanet in a distant galaxy, the mysteries of life beyond Earth continue to inspire and drive our exploration of the universe. The icy shell enveloping Europa, one of Jupiter's moons, serves more than just an aesthetic purpose. It offers crucial protection from the harsh radiation and extreme temperatures that characterize the void of outer space. This thick, frozen layer could function as a natural shield, creating conditions beneath it that may be far more hospitable to life than previously imagined. Beneath the icy exterior lies a vast subsurface ocean, and scientists are increasingly convinced that this hidden water world could harbor the basic elements necessary for life: organic molecules, essential nutrients, and other biochemical components that life relies on to evolve. In fact, future missions to Europa may focus specifically on exploring this ocean. One such avenue of investigation involves analyzing the plume eruptions that spacecraft have observed, which could offer direct access to the moon's subsurface. With these missions, scientists hope to obtain samples from beneath the ice, elevating our understanding of the conditions that could support life beyond Earth. If life does exist on Europa, it could radically shift our conception of life's potential reach across the cosmos, positioning the moon as a central player in the ongoing search for extraterrestrial life. This search for life extends far beyond Europa. Meteorites, these ancient messengers from the far reaches of space, have long piqued human curiosity. They carry with them tantalizing clues about life's potential on other worlds, as well as offering insight into the building blocks that might be common throughout the universe. Since humanity first gazed up at the stars, meteorites have sparked imagination and speculation about life beyond our planet. When scientists examine meteorites, they often find that many contain organic compounds, the very ingredients that form the basis for life. One particularly significant group of meteorites, known as carbonaceous chondrites, stands out in this cosmic quest. These space rocks have been found to contain amino acids, the fundamental building blocks of proteins, suggesting that the chemistry necessary for life could be far more widespread than we ever anticipated. These findings have pushed scientists to consider an even bolder idea, that the components for life may have originated in space, traveling across the cosmos before being delivered to planets like Earth during their formative years. This theory, known as Panspermia, proposes that microscopic life forms such as bacteria or spores could survive the extreme conditions of space. These tiny organisms might hitch a ride on meteoroids, comets, or even interstellar dust particles. When these celestial bodies collide with planets, they could deposit this life-giving cargo, seeding new worlds with the necessary ingredients for life to take root. The potential for life to travel between planets is supported by the discovery of extremophiles, organisms that thrive in conditions previously thought to be inhospitable. These resilient life forms have been shown to endure extreme heat, intense radiation, and frigid temperatures, suggesting they might survive the harsh journey through space, protected within the rocky or icy shields of meteorites. In fact, some researchers speculate that ancient meteor impacts may have played a crucial role in delivering vital organic materials to Earth, raising intriguing questions about our own origins and the interconnectedness of life across the universe. Some even entertain the possibility that complex life could travel in this manner. While this remains a subject of intense debate, the idea that life on Earth could have extraterrestrial roots challenges our understanding of biology and raises profound questions about the cosmic origins of species. These theories have far-reaching implications, not just for astrobiology, but for the very nature of life itself, suggesting that life may be a cosmic phenomenon, not confined to any one planet, but scattered across the vast expanse of the universe. Experimental evidence has further fueled these ideas. Certain life forms, including bacteria and other microorganisms, have been shown to survive exposure to the vacuum of space and cosmic radiation. These experiments provide tantalizing clues that life may not only be more resilient than we thought, but also more widespread across the cosmos. As we continue to push the boundaries of exploration and understanding, the implications of panspermia open new avenues for scientific inquiry, challenging us to reconsider the nature of life and the potential for its existence beyond our planet. All these discoveries are intertwined with the profound questions that drive the search for extraterrestrial life. The Drake equation, first proposed by astronomer Frank Drake in 1961, serves as one of the key frameworks in our quest to understand the potential for life beyond Earth. This equation attempts to estimate the number of civilizations in our galaxy with which we might be able to communicate. It takes into account various factors such as the rate of star formation, the likelihood that stars have planets, and the chances that life could develop on those planets. The equation highlights the complexity of life's emergence. There are so many variables at play that the equation's conclusions are full of uncertainties. Each term in the equation represents a question, a facet of the cosmic puzzle that scientists continue to investigate. But with the discovery of thousands of exoplanets, planets located outside our solar system, researchers are refining their estimates. Some of these planets reside within their stars' habitable zones, where conditions could be just right for liquid water and, by extension, life to exist. The continued discovery of exoplanets and the possibility that many of these planets could support life fuel optimism about our ability to find life beyond Earth. As we learn more about distant worlds, we gain new perspectives on the universe's potential to harbor life. While the answers may not come easily or quickly, the search for life beyond our planet is one of the most exciting and transformative pursuits of modern science, one that promises to reshape our understanding of our place in the cosmos. The Drake equation compels us to contemplate what truly defines life and how it may manifest in ways we cannot yet fully imagine. Traditionally, the factors outlined in the equation have focused on carbon-based, Earth-like scenarios. However, this perspective is gradually expanding, urging astrobiologists to rethink what constitutes life. The search for extraterrestrial life now includes the possibility that organisms could thrive in environments completely different from our own, potentially biochemically distinct from anything we are familiar with. This broader view helps to push the boundaries of our understanding and fosters collaboration among scientists from a variety of disciplines. Each expert, from biochemists to astronomers, brings invaluable insights that bridge gaps in our knowledge. Moreover, the equation underscores an essential point. Technological development and global cooperation are central to the search for life beyond Earth. As our tools and methods evolve, so does our capacity to scan the vastness of the cosmos in search of signs of life. This pursuit is not just about discovering intelligent civilizations, but also about deepening our understanding of our own place in the universe. With each refinement of our techniques, the exploration of life beyond Earth becomes ever more captivating, reminding us that we are part of a grand cosmic narrative. Astrobiologists are increasingly turning to biochemistry as a key tool in their exploration of alien life forms. By studying the building blocks of life as we understand them on Earth, scientists are able to construct models of alien ecosystems. The starting point of this work is the identification of biosignatures, molecules or chemical patterns that indicate the presence of life. By analyzing the biochemical functions of terrestrial life forms, researchers are able to hypothesize how alien biochemistry might function, particularly in environments vastly different from those found on Earth. The study of extremophiles, organisms that thrive in extreme environments such as boiling hot springs or deep-sea hydrothermal vents, has proven especially useful in this regard. These organisms challenge our assumptions about where life can exist. They reveal that life is far more adaptable and resilient than we once thought, able to flourish in conditions previously deemed inhospitable. This understanding has opened the door to the possibility that extraterrestrial life could also possess a completely different set of biochemical processes to survive in extreme environments on distant planets or moons. In parallel, advancements in computer simulations have become an indispensable tool for scientists. By inputting data on known biochemical processes and environmental conditions, researchers can create intricate models that predict how life might evolve in alien ecosystems. These models take into account factors such as temperature, atmospheric composition, and radiation levels, offering a clearer picture of how organisms could adapt over time. By simulating potential interactions between life forms and their environments, scientists are able to make more informed predictions about where and how life could exist beyond Earth. One of the fundamental aspects of this search is the role of carbon in the formation of life. Carbon is central to the biochemistry of Earth's organisms due to its versatility in bonding with other elements. However, researchers are not limiting themselves to carbon alone. Elements such as silicon are being considered as potential alternatives for alien biochemistry. This broadens the possibilities for life in the cosmos, suggesting that life forms could exist in ways far beyond the familiar carbon-based models that we know so well. In recent years, the discovery of exoplanets, planets that orbit stars outside of our solar system, has provided extraordinary new insights into the potential for intelligent life elsewhere in the universe. This search began in earnest in the mid-1990s and has accelerated with advancements in technology. To date, thousands of exoplanets have been identified, some of which lie in what is known as the habitable zone around their stars. This is the region where conditions might allow for the presence of liquid water, a critical ingredient for life as we understand it. Among the most promising of these exoplanets is Kepler 186f, an Earth-sized planet that orbits its star within the habitable zone, receiving a similar amount of sunlight as Earth does from the Sun. Its size and distance from its star suggest it could maintain liquid water on its surface, offering a tantalizing possibility that life could exist there. Another notable exoplanet is Proxima Centauri b, which orbits the closest star to our Sun. Although the conditions on this planet remain uncertain, its proximity to Earth makes it an intriguing candidate for future study. Beyond just being in the habitable zone, the composition of a planet's atmosphere plays a crucial role in determining its ability to support life. The detection of gases such as oxygen, methane, and carbon dioxide, using techniques like spectrometry, can provide valuable clues about the biological processes occurring on that planet. The recent launch of the James Webb Space Telescope has significantly enhanced our ability to study these distant atmospheres, providing scientists with a clearer view of the chemical makeup of exoplanetary atmospheres. This could help us understand whether the necessary ingredients for life are present. These discoveries ignite the imagination and provoke deep questions about our place in the universe. As we continue to analyze exoplanets and their atmospheres, the dream of answering the age-old question of whether we are alone in the cosmos draws ever nearer. The possibility that intelligent life exists elsewhere motivates our exploration of space and underscores the delicate balance of conditions necessary for life to thrive. On Earth, the study of oceanic organisms in extreme environments provides invaluable clues to the potential for life beyond our planet. Remarkable creatures found in deep-sea hydrothermal vents or frigid polar regions reveal that life can endure in conditions once thought to be inhospitable. By studying these organisms, scientists gain essential insights into the types of environments that could support life, even in the most extreme settings. Among the most fascinating examples of extremophiles are tube worms found near hydrothermal vents. These organisms thrive in the intense heat and pressure of the ocean floor, relying on chemosynthesis rather than photosynthesis to generate energy. They convert chemicals spewing from the Earth's crust into food, demonstrating that life can use entirely different energy sources to survive. This adaptability expands the possibilities for what alien life forms might look like, particularly on moons like Europa or Enceladus, where subsurface oceans are hidden beneath icy surfaces. If life can thrive in such extreme conditions here on Earth, it is not hard to imagine similar life forms existing in the most remote corners of the universe. The genetic and physiological diversity found among the organisms of the oceans offers not just insight into Earth's own evolutionary processes, but also serves as a key resource for scientists pondering life beyond our planet. By investigating how these extraordinary creatures have adapted to survive in some of the harshest environments known to humanity, researchers can begin to theorize how life might emerge and thrive on planets or moons with conditions far more extreme than those of Earth. The extreme adaptations these organisms display, whether it's the ability to withstand crushing depths, freezing temperatures, or total darkness, offer a glimpse into what life forms on alien worlds might look like and how they could survive in environments with chemical compositions and atmospheric conditions vastly different from what we know. In fact, some of these organisms feature biochemical pathways that were once thought to be impossible. The discovery of such processes has profound implications for the field of astrobiology, the study of life beyond Earth. As humanity sends missions to icy moons like Europa or distant planets such as Mars, the findings about Earth's deep-sea creatures could shape how scientists approach the search for extraterrestrial life. What was once considered bizarre or highly specialized on Earth may, in fact, provide the missing piece to understanding what life could be like in the cold, isolated reaches of space. This knowledge is not just of theoretical interest. It actively informs the methods and technology used in space exploration, pushing us closer to answering the age-old question, are we alone in the universe? Equally intriguing, though, are the mysteries that linger in the field of cosmology. The study of the universe on the grandest scales reveals deep complexities that defy our best efforts to understand. Despite decades of research, some of the universe's most profound enigmas remain unsolved. Among them is dark matter, an invisible substance that makes up about 27% of the universe's total mass energy content. Though its presence is inferred from its gravitational effects, such as the way galaxies rotate and how light bends around massive objects, its true nature remains elusive. Despite being a fundamental component of the cosmos, dark matter has never been directly detected, leaving scientists to grapple with the unknown. Even more elusive is dark energy, which is believed to account for roughly 73% of the universe's total energy. Dark energy is responsible for the accelerated expansion of the universe, a phenomenon that was first observed in the late 20th century. Its mysterious force pushes galaxies apart at an ever-increasing rate, yet we are still far from understanding what dark energy actually is. Various theories abound, from quantum fields to modifications of gravity, but no consensus has emerged. This unknown force raises fundamental questions about the underlying structure of the universe and its eventual fate. Compounding these cosmic mysteries are the puzzles posed by the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. While we've captured incredibly detailed images of this ancient relic, questions still linger about the uniformity of the CMB and whether small fluctuations might point to the existence of phenomena beyond our current understanding. These minute variations could offer clues to the early conditions of the universe and might even hint at the existence of other dimensions or alternate aspects of the cosmos. Decoding the information embedded in these cosmic relics is an ongoing challenge, one that keeps scientists engaged and searching for new tools and techniques to unlock its secrets. Among the most captivating and mind-bending concepts in cosmology today is the idea of the multiverse, the theory that our universe is just one of many, each existing in its own bubble of spacetime. If this theory proves true, it would fundamentally alter our understanding of reality. But proving the existence of parallel universes remains a formidable challenge, and it is a topic of debate and speculation, with many scientists eager for breakthroughs that could provide evidence of these alternate realities. The multiverse could explain numerous phenomena that currently elude our understanding, but we are still far from developing the technology and methodology to explore this possibility fully. Meanwhile, another area of cosmic inquiry involves the study of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Their origins continue to baffle researchers. Most of these particles originate outside our solar system, and some are believed to come from distant galaxies. Supernovae, the explosive death throes of massive stars, are one potential source, as they release shock waves that accelerate particles to nearly incomprehensible speeds. Neutron stars, the remnants of supernovae, also contribute to the cosmic ray phenomenon. Their extreme density and powerful magnetic fields generate high-energy particles that can traverse vast distances through space. What makes cosmic rays so fascinating is not just their origin, but their composition. While many of them are protons, a significant number are heavier atomic nuclei or even electrons, leading scientists to wonder how these particles are accelerated to such extreme energies. The most puzzling of these are the ultra-high energy cosmic rays, which defy the expectations of modern particle physics. The energies of these particles are so high that they challenge our current understanding of physics, and scientists are constantly seeking to uncover the processes that generate such extraordinary energies. The way cosmic rays interact with Earth's atmosphere provides yet another layer of intrigue. When they collide with air molecules, they create showers of secondary particles that cascade down to the surface. By studying these secondary particles, researchers can gain valuable insights into the nature of cosmic rays themselves, and by extension, the astrophysical processes that produce them. Ground-based detectors, which capture these cascades, play a crucial role in advancing our understanding of cosmic rays and their origins. Unraveling the mysteries of cosmic rays is not just about tracing the origins of these particles, it also offers a window into the fundamental processes of the universe itself. Each discovery raises new questions, making cosmic ray research an exciting intersection of astrophysics, particle physics, and cosmology. As we continue to explore this enigmatic phenomenon, we edge closer to a deeper understanding of the cosmos. Then there is the Fermi paradox, a concept that sits at the intersection of cosmology and the search for extraterrestrial intelligence. Named after the physicist Enrico Fermi, this paradox highlights a striking contradiction. While the universe is vast, containing billions of galaxies and potentially habitable planets, we have yet to find any definitive evidence of intelligent extraterrestrial civilizations. The sheer number of stars and planets in the habitable zone of their respective stars leads one to expect that alien life should be abundant. And yet, despite extensive searching, we seem to be alone in this infinite expanse of space. This paradox invites a number of questions about the nature of technological civilizations. Could intelligent species inevitably self-destruct before they are able to communicate across the vastness of space? History here on Earth suggests that the rise and fall of civilizations is a recurring pattern. From ancient empires to modern nations, human history is littered with the stories of once great societies that vanished. This trend raises the possibility that the emergence of advanced technological civilizations is not a foregone conclusion, but a precarious journey fraught with existential risks. The Fermi paradox serves as a profound reminder of our place within the vast, intricate expanse of the universe. It compels us to consider the sustainability of our civilization, urging us to safeguard our planet for future generations. As we peer into the infinite stretch of the night sky, we are not merely seeking company among distant stars. Rather, we are confronted with the far more pressing challenge of ensuring the survival of our own species. The universe, teeming with possibility, is also shrouded in an unsettling mystery, forcing us to examine what it truly means to be a responsible player in a cosmic theater where the rules are still being discovered. One of the most captivating phenomena that beckon us to explore the mysteries of space are pulsars, celestial objects that behave much like cosmic lighthouses, casting beams of radiation across the vastness of the universe. These extraordinary neutron stars are not only rotating at incredible speeds, but are also highly magnetized, emitting electromagnetic radiation across a spectrum that includes radio, visible, and even gamma rays. As a pulsar spins, its lighthouse-like beam becomes visible from specific angles, much like the rotating light of a traditional lighthouse is only visible from certain positions along the shore. When Earth aligns with the path of one of these beams, observers on our planet detect regular, almost mechanical pulses of radiation, each pulse occurring with remarkable precision. These rapid rotations, often completing a full cycle in mere milliseconds, create a steady rhythm that astronomers can measure with extraordinary accuracy. This precision allows scientists to use pulsars as cosmic clocks, providing a stable reference for measuring time and aiding in navigation across deep space. Beyond their function in cosmic navigation, pulsars also offer insights into some of the universe's most extreme conditions. These dense remnants of massive stars, created when those stars undergo supernova explosions, contain materials so dense that a mere teaspoon of pulsar material would weigh as much as a mountain here on Earth. Such extreme densities allow researchers to explore the behavior of matter under conditions that are far beyond what we can replicate in laboratories. By understanding how matter behaves in these high-density environments, scientists can unlock fundamental truths about particle physics and the state of matter under extraordinary pressures. The intricate dynamics of pulsars also provide valuable clues about the interstellar medium, the gas and dust that fill the vast spaces between stars, and the conditions that lead to their formation. Studying pulsars allows astronomers to trace the history of our universe, revealing secrets that stretch back billions of years. Each pulse from a pulsar serves as a brief but significant glimpse into the very nature of space-time and the fundamental forces that govern the cosmos. In addition to the mysteries embedded within pulsars, astronomers have observed peculiar motions of certain celestial bodies that challenge our understanding of gravitational dynamics. These anomalies, unexplained trajectories, and orbital discrepancies cannot be fully accounted for by the known laws of physics. Such irregularities have sparked theories about the presence of unseen mass, giving rise to the concept of dark matter. Unlike ordinary matter, dark matter does not emit light or energy that can be detected directly, yet its gravitational influence seems to shape the structure of galaxies and clusters of galaxies. For example, when scientists study the rotation curves of galaxies, they notice something strange. Stars located on the outer edges of these galaxies rotate at speeds that defy predictions based on the visible matter present. This discrepancy suggests that there is additional, invisible mass influencing their motion. This has led to the hypothesis that dark matter makes up a significant portion of the universe, contributing to the gravitational pull that holds galaxies together. Further evidence of this mysterious substance has surfaced in the form of anomalies in the orbits of certain celestial objects. The unusual motion of the dwarf planet Eris and the suspected existence of Planet 9 at the edge of our solar system may indicate the presence of large, undiscovered planetary bodies, their gravitational influence shaping the orbits of nearby objects. Such theories have inspired new missions and research initiatives, fueling our desire to uncover these cosmic mysteries and revealing deeper truths about our universe. The discoveries surrounding dark matter also touch on larger questions about the composition of the universe and the fundamental laws that govern its behavior. As scientists continue to explore these anomalies, they refine our understanding of gravity, matter, and the very fabric of space-time itself. Each new finding brings us closer to uncovering the unseen forces that shape the universe, offering profound insights into the nature of reality itself. Among the most enigmatic phenomena in modern astrophysics are the fast radio bursts, brief, powerful pulses of radio waves that originate from distant galaxies. First detected in 2007, these bursts have puzzled scientists, leading to a range of hypotheses about their origin. Some proposed explanations include cosmic events such as neutron star collisions or interactions with magnetars, highly magnetized neutron stars. The true source of these bursts, however, remains a mystery. What makes them so fascinating is not just their explosive energy, but their unpredictability. These millisecond-long flashes of radiation can release more energy than the entire output of a galaxy, prompting scientists to reevaluate their models of astrophysical phenomena. The sporadic nature of these bursts, seemingly random in occurrence, adds another layer of intrigue as researchers struggle to understand the mechanisms driving such powerful emissions. As scientists continue to investigate fast radio bursts, they are not only seeking answers about the origin of these signals, but also gaining valuable information about the environments through which they travel. The study of these bursts allows astronomers to probe the intergalactic medium, enhancing our understanding of the vast invisible matter that fills the spaces between galaxies. With each new discovery, fast radio bursts push the boundaries of our knowledge, challenging our current understanding and opening new avenues for scientific exploration. In a similar vein, the search for dark galaxies, the elusive structures that seem to lack the visible stars typically found in brighter counterparts, has captured the imagination of astronomers for years. Evidence for the existence of these dark galaxies comes primarily from the gravitational effects observed in regions of space where visible matter seems insufficient to account for the movements of stars and gas. By studying the motions of these objects, scientists have inferred the presence of additional unseen mass, likely dark matter, that exerts a gravitational influence on its surroundings. Techniques like gravitational lensing, in which light from distant objects is bent around a massive gravitational source, have provided further evidence of these hidden galaxies. Dark galaxies, believed to contain substantial amounts of dark matter, remain a tantalizing puzzle for astronomers. Their gravitational influence shapes the universe around them without emitting any detectable light. Investigating these galaxies not only helps us understand the nature of dark matter, but also provides deeper insights into the processes that govern the formation and evolution of galaxies themselves. As our technological capabilities improve and new observational techniques emerge, the mysteries surrounding dark galaxies and the forces that govern them may soon reveal some of the most profound secrets of the cosmos. In each of these cases, the pulsars, dark matter, fast radio bursts, and dark galaxies, astronomers are peering into the unknown, challenging our existing models of the universe and pushing the boundaries of our understanding. Each discovery, no matter how small, contributes to a larger narrative about the nature of reality, the forces that shape the cosmos, and the role we, as human beings, play in this vast and mysterious universe. As we continue to explore the cosmos, we are reminded that there is so much more to discover, answers that may forever change how we perceive the world around us. Radio telescopes, with their unique ability to observe distant phenomena through radio waves, have revealed an intriguing and mysterious aspect of our universe: cold gas clouds that do not correspond to any known visible galaxies. These clouds, often rich in hydrogen, have sparked significant interest in the astronomical community, as they may be remnants of galaxy formation. Their lack of stars, however, hints that these regions of space have not yet developed into star-forming entities. The discovery of these cold gas clouds is a crucial piece of evidence supporting the hypothesis that a population of galaxies exists predominantly in a dark matter state. These galaxies, while theoretically present, are virtually invisible in conventional observations and appear to have little or no potential for star formation. It is possible that this absence of activity is not permanent, but rather a phase in the galaxy formation process where the clouds are in a primordial state, slowly evolving over vast periods of time. As astronomers piece together the various strands of evidence from radio telescopes and other observational tools, they are beginning to form a more complex and nuanced picture of the universe. Far from the simplistic view that was once held, it appears that our cosmos is teeming with invisible structures, many of which may remain undetected until future technologies can reach them. The existence of these dark galaxies resting quietly in the vast expanse of space challenges the conventional understanding of galaxy formation and evolution. This raises profound questions about how galaxies form, how they develop over time, and whether the processes we observe in our own galaxy are universal or unique. With each new discovery, researchers continue to refine their techniques and technologies, delving deeper into the secrets of these elusive dark galaxies. What we once thought we understood about the universe is continually evolving as we uncover more about its hidden layers. These, as ongoing investigations, hold the promise of exciting breakthroughs that could change our understanding of the cosmos forever. Saturn's rings have long captured the imagination of both scientists and the general public alike. Their breathtaking beauty, coupled with their complex and mysterious nature, makes them a fascinating subject of study. Comprised of billions of icy particles, rocky debris, and fine dust, the rings present a striking visual contrast to the planet's golden hue. But beyond their visual allure lies a deeper scientific mystery: the origin and formation of these iconic rings. One of the most compelling theories suggests that Saturn's rings were formed from a moon that was torn apart by the planet's immense gravitational forces. However, while this idea is widely accepted, the exact events that led to the formation of the rings remain elusive. There is still much to learn about the forces at play and the processes involved in the creation of such a vast and intricate ring system. Another puzzling question concerns the age of Saturn's rings. While Saturn itself has existed for over 4 billion years, some researchers propose that the rings may be much younger, possibly only a few 100 million years old. This discrepancy in age raises important questions about the history of the Saturnian system and the longevity of the rings. If the rings are indeed relatively young, they offer a unique snapshot of the dynamic processes occurring in our solar system, giving us a rare glimpse into the evolution of planetary systems. This age difference also prompts discussions about the rings' future. If they are young, how long will they last? Will they continue to evolve, or are they on the brink of disintegration? These questions point to the broader dynamics of celestial bodies and how the interactions between planets, moons, and debris shape the environments in which they exist. Furthermore, studying Saturn's rings offers valuable insights into the fundamental laws of physics, particularly in the realm of gravitational interactions. The sharp edges and gaps within the rings, along with their overall structure, raise fascinating questions about the forces governing them. For instance, the presence of tiny moonlets within the rings may be influencing the distribution of material, creating a delicate balance that scientists are only beginning to understand. This intricate dance between gravity and motion helps researchers explore how planetary ring systems form and evolve. Saturn's rings, therefore, serve not only as a captivating visual phenomenon, but also as a natural laboratory for planetary science. By studying the interactions between the rings and Saturn's many moons, astronomers gain a better understanding of how celestial bodies influence each other. These findings extend far beyond Saturn itself, providing crucial insights into ring systems on other planets and even in other star systems. As scientists continue their investigations, Saturn's rings offer a rich field of study that continues to deepen our knowledge of the universe and the forces that govern it. One of the most profound mysteries that still captivates humanity is the so-called Great Silence of the universe. Despite the vastness of the cosmos, with billions of galaxies and countless stars, many of which may host potentially habitable planets, we have yet to find definitive evidence of intelligent extraterrestrial life. This apparent paradox has led to much speculation and theorizing about why we have not yet made contact with civilizations beyond Earth. One prominent explanation is known as the Fermi paradox, which highlights the contradiction between the high probability of intelligent civilizations existing in the universe and the complete lack of evidence for such civilizations. The paradox raises several possibilities. One is that intelligent life is exceedingly rare, and the conditions needed for the development of complex, technologically advanced societies may be far more specific than we have previously thought. Another possibility is that civilizations tend to self-destruct before they can make contact with other civilizations. Factors such as nuclear war, climate change, or uncontrolled technological advances might lead to the premature extinction of advanced societies, preventing them from communicating across interstellar distances. Furthermore, the technological challenges involved in establishing communication across the vast expanses of space complicate the search for extraterrestrial civilizations. It is possible that intelligent life exists, but the methods they use to communicate are beyond our current understanding or capabilities. They may not be using radio waves, the primary medium we currently search for, and could be employing communication technologies that are far more advanced or entirely different from what we are capable of detecting. Additionally, the immense distances between stars mean that signals could take thousands or even millions of years to reach us. As a result, we may be missing signals that are already very old by the time they arrive at Earth. The concept of the Great Filter further complicates our understanding of extraterrestrial life. This theory suggests that at some point in the evolution of intelligent life, there is a significant barrier that most civilizations fail to overcome. This filter could lie ahead of us, in which case humanity might face extinction due to some cosmic or self-inflicted catastrophe. Alternatively, the filter could have already occurred in our past, meaning that while many planets may have hosted life, few, if any, have progressed to the stage of technological advancement necessary for interstellar communication. Each of these theories presents a different perspective on the Great Silence and provides a deeper understanding of why we have not yet encountered extraterrestrial intelligence. The mystery raises not only scientific questions, but also philosophical reflections on our place in the universe and the future of human civilization. Finally, the discovery of the cosmic web structure has revolutionized our understanding of the universe's evolution. The cosmic web is a vast, interconnected network of galaxies, gas, and dark matter, held together by gravity and forming a web-like arrangement across the entire cosmos. This intricate structure offers a powerful insight into the forces that have shaped the universe since the Big Bang. The origins of the cosmic web can be traced back to tiny fluctuations in the density of matter shortly after the Big Bang. These small variations allowed gravity to exert its influence, gradually pulling matter together to form the massive structures we observe today. As time passed, areas of higher density attracted more matter, leading to the formation of galaxy clusters, while vast voids, regions with fewer galaxies, also emerged. This dynamic process of gravitational attraction continues to shape the universe, with matter constantly being pulled into new structures and patterns. The cosmic web provides us with a glimpse into the universe's ongoing evolution. It demonstrates that the cosmos is not a static, unchanging entity, but rather a dynamic, ever-evolving system. The interconnectedness of galaxies, gas, and dark matter within the web highlights the fundamental forces that govern the cosmos and offers profound insights into the ongoing processes of cosmic evolution. Understanding the cosmic web not only helps explain the current state of the universe, but also offers clues about its past and future, revealing the complex and ever-changing nature of the cosmos. The role of gravity in shaping the cosmic web is crucial, but it is far from the only force influencing the universe's structure. In fact, dark matter, although invisible and undetectable by conventional means, plays a fundamental role in shaping the universe on a grand scale. Dark matter makes up a significant portion of the universe's total mass, and it is believed to be primarily responsible for the structure of the cosmic web. This web is a vast interconnected network of galaxies and other cosmic structures that stretches across the universe. It illustrates the symbiotic relationship between visible matter, which makes up galaxies, stars, and planets, and the invisible, yet immensely powerful, dark matter that binds it all together. Together, these forces reveal an intricate dance of gravitational interactions, where visible and invisible matter work in tandem to shape the universe's evolution. Recent studies of the cosmic web, fueled by advanced simulations and observations from some of the most powerful telescopes in the world, have provided compelling evidence supporting our understanding of cosmic evolution. These studies help us peer into the distant past, unlocking the mysteries of how galaxies and clusters of galaxies formed and how they continue to evolve. They not only reveal the history of the universe, but also offer insights into its future trajectory. As galaxies continue their slow drift through the cosmic web, they are destined to collide, merge, or even drift apart. These interactions will profoundly affect their growth, structure, and behavior. This ongoing cosmic evolution is a testament to the intricate interplay of forces that have shaped the universe and will continue to guide its development for billions of years to come. The foundation of our astronomical knowledge wasn't built overnight. It evolved over thousands of years. Many ancient civilizations contributed to our understanding of the cosmos, with their observations and theories laying the groundwork for future advancements. Among the first were the Babylonians, who carefully observed the night sky and recorded celestial events on clay tablets. Their meticulous calculations of the positions of planets and phases of the moon were among the earliest forms of astronomy, serving as a springboard for subsequent civilizations. The ancient Egyptians, too, made significant strides in understanding the heavens. Their construction of the pyramids was aligned with certain stars, particularly Sirius and Orion, demonstrating a sophisticated grasp of the cosmos. They used the rising of Sirius to predict the annual flooding of the Nile River, a vital event for their agriculture, and their observations of the stars reflected an intimate relationship between astronomy and daily life. Similarly, the Maya civilization in Mesoamerica made extraordinary contributions to astronomy, developing complex calendars based on their observations of the stars, planets, and lunar cycles. Their ability to predict solar and lunar eclipses and their precise records of planetary movements were remarkable feats of astronomical science. Their understanding of the cosmos was so advanced that it was woven into their religious beliefs, further underscoring the deep connection between their cultural practices and the celestial world. As centuries passed, Greek philosophers and scientists built upon the knowledge of these earlier civilizations. Figures such as Aristotle and Claudius Ptolemy developed the geocentric model of the universe, which positioned Earth at the center of all creation. This idea held sway for centuries, but it was eventually challenged by new discoveries that would change our understanding of the cosmos forever. Despite their limited technology, early astronomers were able to develop detailed models of the universe. They used geometry and careful observation of celestial bodies to explain phenomena like the phases of the moon and the apparent retrograde motion of planets. The gnomon, a simple tool resembling a vertical stick that casts a shadow, allowed them to measure the sun's position and track solar cycles. critical for understanding timekeeping and agriculture. Though these ancient astronomers lacked the advanced tools of modern science, their observations laid the foundation for future breakthroughs. Their work paved the way for revolutionary thinkers like Copernicus and Galileo, who would eventually dismantle the geocentric model and move toward the heliocentric model of the solar system. This shift marked a turning point in human understanding, with the realization that the Earth was not at the center of the universe, but merely one planet orbiting the Sun. The invention of the telescope in the early 17th century marked a monumental leap in our ability to explore the cosmos. Before its invention, humanity's view of the universe was limited to what could be seen with the naked eye. The telescope, however, enabled astronomers to observe distant celestial objects in unprecedented detail. Galileo Galilei was one of the first to use the telescope to observe the night sky, making groundbreaking discoveries. He observed the moons of Jupiter, revealing that not all celestial bodies revolve around the Earth, a direct challenge to the geocentric model. His observations of sunspots and the phases of Venus provided further evidence for the heliocentric model and transformed our understanding of the universe. The impact of the telescope was profound, and its influence continues to shape our understanding today. Subsequent advancements, such as Isaac Newton's reflecting telescope, allowed for even clearer views of the cosmos. Observatories equipped with these powerful telescopes became critical in cataloging the stars, nebulae, and galaxies that populate the universe. This accumulation of data led to revolutionary theories about the structure and evolution of the universe, such as the discovery that the Milky Way is a spiral galaxy, one of billions in an unimaginably vast cosmos. As technology advanced, so did the capabilities of our telescopes. The development of radio telescopes extended our ability to explore the universe beyond the visible spectrum. These instruments allow us to study cosmic phenomena that emit radio waves, expanding our understanding of the universe's complexities. Telescopes placed in space, such as the Hubble Space Telescope, have further revolutionized our observations, eliminating the interference of Earth's atmosphere and giving us clearer views of distant galaxies and nebulae. With each technological advance, we unlock new layers of knowledge, expanding our cosmic perspective and continually reshaping our understanding of the universe and our place within it. One of the most profound shifts in our understanding of the cosmos came with the Copernican revolution. Prior to this shift, the prevailing belief was that Earth was the center of the universe, a view known as geocentrism. This model, which had been held since ancient times, positioned the Earth at the center, with the sun, moon, and stars revolving around it. This perspective gave humanity a sense of importance, making us believe that we were at the forefront of creation. However, when Nicolaus Copernicus introduced his heliocentric model in the 16th century, everything changed. Copernicus proposed that the sun, not the Earth, was at the center of the universe. This revolutionary idea fundamentally altered our perception of the cosmos. No longer were we the center of the universe, but rather just one of many celestial bodies orbiting the sun. This shift revealed a universe that was not static, but dynamic, interconnected, and filled with infinite possibilities. The heliocentric model had far-reaching implications not only for science, but also for philosophy and religion. It challenged centuries-old doctrines that had placed humanity at the center of the divine order, forcing individuals to reconsider their place in the cosmos. The grandiosity that had once surrounded humanity began to fade, replaced by a more humble understanding of our existence within a vast and ever-expanding universe. The Copernican revolution was the beginning of a new era of scientific inquiry, one in which humanity would continue to push the boundaries of knowledge, seeking to uncover the mysteries of the universe. The dawn of the Copernican revolution stands as one of the pivotal moments in the history of scientific thought, laying the foundation for a profound transformation in humanity's understanding of the cosmos. Before this groundbreaking shift, the prevailing worldview was rooted in ancient traditions and geocentric models, which placed Earth at the center of the universe. However, when Nicolaus Copernicus proposed a heliocentric model, suggesting that the Earth revolved around the sun, it marked not just a revolutionary idea, but a complete overhaul in our approach to understanding the universe. This shift in perspective, emphasizing observation and reason over established dogma, set the stage for an era of unprecedented scientific inquiry. As this new way of thinking began to take root, it paved the way for future astronomers to build upon the insights of Copernicus. Galileo Galilei, with his telescope, observed the moons of Jupiter, challenging the geocentric model even further, while Johannes Kepler refined the heliocentric theory by revealing the elliptical orbits of planets. Their work unraveled mysteries that had eluded mankind for millennia, slowly revealing the true nature of our place in the cosmos. The Copernican revolution was more than just a scientific milestone. It fundamentally reshaped the way we view existence, encouraging humanity to ask profound questions about our role in the universe and the very fabric of reality itself. It highlighted the humbling reality that we are just a small part of a vast, ever-expanding cosmos, a perspective that continues to inform our understanding of the universe to this day. As the centuries progressed, the 20th century emerged as a transformative period for cosmology, marked by a series of groundbreaking discoveries that would forever alter the way we perceive space. One of the most significant revelations came in the early 1900s, when Albert Einstein introduced his theory of general relativity. Prior to Einstein's work, gravity was understood as a force acting at a distance, but Einstein's theory proposed that gravity was not just a force, but the curvature of space-time itself, fundamentally changing our understanding of the universe. This paradigm-shifting theory opened up new possibilities for exploring the cosmos, laying the groundwork for the discovery of black holes, the expansion of the universe, and phenomena that were once thought to be beyond human comprehension. In the mid-20th century, another critical discovery further deepened our understanding of the universe. The detection of cosmic microwave background radiation provided compelling evidence for the Big Bang theory, offering a glimpse into the very origins of the universe. This faint afterglow, a relic from the universe's birth, allowed astronomers to peer into the conditions of the early cosmos and trace its expansion over the past 8 billion years. This discovery not only validated the predictions made by earlier cosmological theories, but also launched a new era of observational cosmology, providing us with a richer, more detailed understanding of the universe's evolution. The arrival of space exploration in the mid-20th century introduced a new dimension to our understanding of the cosmos, offering an unprecedented perspective on our solar system and beyond. The launch of satellites and human spaceflights allowed for direct exploration of celestial bodies, leading to remarkable discoveries about the features of planets like Mars, the gas giants, and moons such as Europa and Enceladus, which may harbor environments conducive to life. These missions provided valuable data on planetary geology, atmospheric conditions, and the essential ingredients for life, further expanding our knowledge of the solar system. In parallel, technological advancements such as the development of radio telescopes and deep space observatories have enabled us to observe distant galaxies, nebulae, and other cosmic phenomena. One of the most fascinating discoveries of the modern era has been the identification of quasars, extremely bright objects powered by supermassive black holes. These enigmatic objects, along with the realization that dark matter and dark energy make up the majority of the universe, have challenged our fundamental understanding of the cosmos, driving researchers to seek answers to the deepest questions about the universe's structure and ultimate fate. Each of these scientific revelations has illuminated a more complex and dynamic cosmos, forever altering our quest for knowledge. The mysteries of the universe are vast, and as our understanding evolves, so too does our ability to contemplate the unknown. Science fiction, a genre often seen as speculative and imaginative, has played a crucial role in reflecting humanity's hopes, fears, and aspirations about the universe. From the early works of H.G. Wells and Jules Verne to contemporary films and television series, science fiction has inspired countless individuals to dream about the cosmos and the possibilities of scientific exploration. By imagining futures filled with space travel, alien civilizations, and advanced technologies, science fiction not only entertains, but also sparks curiosity about the mysteries of the universe. One of the most iconic examples of science fiction's impact on our understanding of space is the television series Star Trek. The show introduced audiences to the concept of faster-than-light travel and the notion of a galaxy teeming with intelligent life. Beyond entertainment, Star Trek has had a profound influence on real-world scientific endeavors, inspiring engineers and scientists to develop technologies that have become integral parts of our daily lives, such as mobile phones and tablet computers. The series also made complex scientific concepts more accessible to the public, facilitating discussions about extraterrestrial life, artificial intelligence, and the potential of interstellar travel. Moreover, science fiction often delves into moral and philosophical questions surrounding the rapid pace of technological advancement. Works like Arthur C. Clarke's 2001: A Space Odyssey provoke thought on the nature of human evolution, the role of artificial intelligence, and the broader implications of our relationship with technology. By posing these complex ethical dilemmas, science fiction encourages deeper reflection on the potential consequences of our discoveries, urging scientists, policymakers, and the general public to consider the long-term ramifications of their actions. As scientific knowledge continues to advance, science fiction remains a vital force in shaping public perceptions of what is possible. It bridges the gap between imagination and reality, inspiring future generations of scientists while framing the discussions we have about our collective future in space exploration. The ancient stone circle of Stonehenge, situated on the Salisbury Plain in England, has long captivated the imagination of scholars, historians, and visitors alike. For over 5,000 years, this remarkable structure has stood as both an archaeological wonder and a symbol of humanity's early understanding of the cosmos. While its precise purpose remains the subject of debate, many theories suggest that it was a site for celestial observance, a burial ground, or even an early form of calendar designed to mark seasonal changes. One of the most intriguing features of Stonehenge is its alignment with the movements of the sun and moon. During the summer solstice, the rising sun casts its rays directly through the entrance of the stone circle, illuminating the central altar stone. This phenomenon suggests that the builders of Stonehenge possessed an advanced knowledge of solar cycles, indicating a sophisticated understanding of astronomy. The alignment with the setting sun during the winter solstice further suggests that Stonehenge may have played a role in rituals tied to death and rebirth, a powerful connection to ancient beliefs about the cycles of nature. The design of the stone circle itself, along with the surrounding earthworks, reveals a deliberate effort to integrate the structure with the landscape. Some researchers propose that the positioning of the stones may have been intentionally aligned with specific stars, imbuing the site with a deeper cosmological significance. This alignment points to the belief systems of the ancient people who constructed Stonehenge, revealing their desire to connect with the heavens and understand their place in the universe. Excavations at nearby sites, such as Avebury, have uncovered further evidence of a broader network of sacred spaces, suggesting that Stonehenge was part of a larger ritualistic and astronomical landscape. Despite significant progress in understanding its construction and potential uses, many questions remain unanswered. Did the builders leave behind any records? Or has much of their knowledge and intent been lost to time? As new technologies and methods of excavation continue to shed light on Stonehenge, each discovery brings us closer to understanding the deeper connections between our ancestors and the cosmos. Stonehenge's allure endures, attracting researchers, visitors, and seekers alike, all drawn to the mysteries it holds. As we continue to explore the ancient monument's astronomical significance, we are reminded of the timeless human quest to understand the universe and our place within it. The invention of the spectrograph in the late 19th century revolutionized the field of astronomy, providing scientists with an entirely new tool for studying the nature of celestial bodies. Prior to this development, astronomers were limited to visual observations and the information they could glean from the naked eye. However, with the advent of the spectrograph, astronomers were able to analyze the light emitted, absorbed, or scattered by objects in space, unveiling a wealth of information about the universe. The spectrograph works by dispersing light into its component wavelengths, much like a prism creates a rainbow. This analysis allows scientists to determine key characteristics of distant stars and galaxies, such as their temperature, composition, and even their motion. By studying the spectral lines produced when light interacts with matter, astronomers can identify specific elements and compounds within these distant objects, revealing their chemical makeup. Through this technological leap, the spectrograph has enabled us to study stars that are light years away, opening up new possibilities for understanding the very nature of the universe. With each new discovery, our understanding of the cosmos deepens, offering a more intricate and nuanced view of the universe. The history of space exploration and scientific inquiry is a testament to humanity's relentless pursuit of knowledge and our unyielding desire to unravel the mysteries of the universe. From the ancient builders of Stonehenge to the modern-day scientists probing the depths of space, our quest to understand the cosmos continues to inspire generations, driving humanity toward new frontiers of discovery. The advent of the spectrograph marked a monumental shift in our ability to explore the universe, opening up unprecedented avenues for the discovery of phenomena that were once invisible to human eyes. A key example of this is the Doppler effect, which allows astronomers to measure the velocity of stars and galaxies relative to Earth by observing shifts in the spectral lines of light. This seemingly simple tool has had far-reaching consequences. It provided vital evidence for the expanding universe and subsequently led to the groundbreaking discovery of dark energy, two revelations that radically altered our understanding of cosmology. These concepts are not just historical footnotes. They continue to influence the course of modern astrophysics today. As technology has advanced, so too have spectroscopic techniques, enhancing both observational methods and the theoretical frameworks that support them. This evolution has significantly deepened our understanding of the cosmos, expanding our knowledge of everything from the life cycle of stars to the complex dynamics of distant galaxies. In the future, as technology continues to improve, spectroscopic tools are poised to offer even more profound insights, ensuring that the cosmos will continue to unfold its mysteries through the language of light. The history of astronomical discoveries is a rich tapestry woven together with significant historical milestones that have fundamentally reshaped our view of the universe. One of the earliest and most transformative moments in this journey was the invention of the telescope in the early 17th century. This invention marked the dawn of a new era in astronomy, enabling humans to peer into the vast expanse of space and uncover celestial truths that had previously been beyond reach. In 1609, Galileo Galilei turned his newly constructed telescope toward the night sky, making groundbreaking discoveries that would forever alter our understanding of the cosmos. He observed moons orbiting Jupiter and noted the phases of Venus, both of which provided early evidence that not all celestial bodies revolved around the Earth. This was a pivotal challenge to the geocentric worldview that had dominated for centuries, setting the stage for the scientific revolution. Further breakthroughs came just a few decades later in 1631, when Johannes Kepler, building on the observational data of his mentor Tycho Brahe, formulated his laws of planetary motion. Kepler's work refined our understanding of planetary orbits and laid the groundwork for the law of universal gravitation, which Isaac Newton would later formalize in the late 17th century. This confluence of discoveries marked a profound shift in our understanding of celestial mechanics, from a largely philosophical and observational framework to one grounded in mathematics and physics. These insights forever changed the trajectory of scientific thought, steering it toward a more rigorous, evidence-based approach to understanding the universe. The 18th century continued this trend of discovery, with William Herschel's 1781 identification of the planet Uranus. This was the first planet to be discovered with a telescope, expanding our knowledge of the solar system and sparking a wave of interest in the outer reaches of space. Herschel's discovery was more than a scientific triumph. It ignited the imaginations of astronomers and the general public alike, fueling further exploration of the distant planets and eventually laying the foundations for the field of astrophysics. The 20th century saw an even deeper exploration of the cosmos, with Edwin Hubble's 1924 discovery of galaxies beyond our own Milky Way being a pivotal moment. His observations revealed that the universe was far more vast and expansive than anyone had previously imagined, leading to the formulation of Hubble's law, which describes the expansion of the universe. This discovery not only transformed our understanding of the cosmos, but it also paved the way for revolutionary theories such as the Big Bang theory, which proposes that the universe originated from a single infinitely dense point in time. These scientific milestones have reshaped both our understanding of the universe and our place within it, with each discovery building upon the last, compounding our sense of awe and curiosity. Beyond the realm of Western scientific exploration, indigenous cultures around the world have long maintained rich and diverse interpretations of celestial events. For many of these cultures, the night sky was not merely a navigational tool, but a profound spiritual canvas, intricately woven into daily life, rituals, and storytelling. The movements of celestial bodies were often seen as manifestations of ancestral spirits or de-shaping agricultural practices, seasonal events, and ceremonial activities. Take, for example, the Mayan civilization, which developed one of the most sophisticated astronomical systems of the ancient world. The Maya meticulously tracked the cycles of the moon, planets, and especially Venus, which played a critical role in their calendrical systems. Their careful observations enabled them to predict solar and lunar eclipses, events that were imbued with deep spiritual significance. Eclipses were seen as omens, often prompting ritualistic practices designed to appease the celestial forces believed to govern the universe. The Mayans' ability to align their understanding of the heavens with their daily lives and cultural practices is a testament to their profound connection to the cosmos. Similarly, the Aboriginal peoples of Australia have maintained a deep spiritual and cultural connection to the stars. For thousands of years, they have used the stars not only as navigational tools to guide their hunting and gathering, but also as repositories of cultural knowledge and moral teachings. Through a rich oral tradition, the Aboriginal people have passed down stories that explain the positions of stars and constellations, embedding valuable lessons about life, the environment, and social customs within these narratives. For them, the sky is a living library, an archive of both past events and future directions, written in the stars for all to see. In the far northern regions, indigenous communities, including those in the Arctic, have their own unique interpretations of celestial events. The aurora borealis, or northern lights, for example, is often seen as a form of communication from the ancestors. The celestial dances of the aurora were interpreted in various ways, with many cultures viewing the lights as messages, blessings, or even warnings. In these harsh, remote regions, understanding the cycles of celestial events was not just a matter of curiosity, but a matter of survival. The movement of the stars, the changing of the seasons, and the appearance of the auroras were crucial for navigation, seasonal hunting, and cultural identity. The interplay between the stars and daily life underscores the deep respect these communities have for the cosmos, where science and culture blend seamlessly into an enduring dialogue with the heavens. On Earth, the planet's geology plays a significant role in how we interact with cosmic events, particularly meteor strikes. When a meteor enters the Earth's atmosphere, it is subjected to extreme heat and pressure, causing it to disintegrate at high altitudes. This spectacular process creates bright streaks of light in the sky, what we know as shooting stars. These events, though brief, serve as poignant reminders of the dynamic and often violent interactions between our planet and the wider universe. The study of meteorites and their impact on Earth's geological history continues to provide important clues about the origins of our solar system and the cosmic forces that shape it. In essence, the story of humanity's exploration of the universe is one of continuous discovery. Whether through the lens of a telescope or the wisdom passed down through generations of indigenous cultures, our understanding of the cosmos is constantly evolving, shaped by both scientific advancements and the deep-seated connections humans have had with the night sky for millennia. As we look toward the future, the mysteries of the universe continue to beckon, promising new revelations and insights that will further enrich our understanding of the world and our place within it. However, larger meteors are capable of reaching Earth's surface, where their collisions with the ground can generate immense energy, comparable to the explosion of a nuclear bomb. The size and shape of the craters formed by these impacts depend significantly on the composition of the bedrock beneath the surface. The geological features of the area around the impact site also play a key role in shaping the aftermath. For instance, when a meteor strikes rocky terrain, it tends to create sharp, distinct craters. In contrast, impacts on softer surfaces, such as clay or sand, often result in more dispersed and less clearly defined depressions. These differences in geological makeup also influence how shock waves from the impact propagate through the Earth. In certain situations, the shock waves can affect nearby ecosystems, causing significant disruption and even triggering seismic activity. One of the most well-known examples of such an event is the impact that created the Chicxulub crater, approximately 66 million years ago. This colossal meteor strike is widely believed to have played a crucial role in the extinction of the dinosaurs, underscoring how these extraterrestrial collisions can not only leave an indelible mark on the planet's surface, but also alter the course of life on Earth itself. Moreover, Earth's atmosphere serves as a protective barrier, shielding us from smaller meteors that might otherwise cause widespread damage. However, larger impacts continue to pose a substantial threat to both the planet's terrain and its life forms. Over time, Earth's geological processes, such as erosion and tectonic activity, often erase the visible traces of these cosmic events. Nevertheless, these ancient scars serve as a testament to the dynamic and ever-evolving relationship between our planet's geology and the cosmos, highlighting how Earth's surface and its ecosystems have been shaped by forces far beyond our control. Solar flares, sudden and violent bursts of radiation emitted by the sun, also have profound implications for life on Earth, particularly in relation to technology and the atmosphere. These explosive events release energy on a scale comparable to millions of hydrogen bombs. While these bursts of solar energy can be awe-inspiring to witness, they can wreak havoc on the delicate balance of our technological infrastructure. When a solar flare occurs, it sends energetic particles hurtling toward Earth, reaching our planet within minutes. These charged particles interact with Earth's magnetosphere, sparking geomagnetic storms that can interfere with satellite operations, including navigation systems, telecommunications, and satellite imaging. Astronauts aboard the International Space Station are not immune to these effects, as the heightened radiation levels during a solar flare could pose a threat to their health, requiring protective measures while they orbit high above the Earth. Additionally, solar flares can induce electrical currents in power lines, potentially causing dangerous voltage spikes that might overwhelm electrical grids. There have been documented instances where geomagnetic storms have led to power outages, showing how these events can disrupt life on Earth in unexpected ways. The atmosphere itself is also affected by solar flares. These bursts of energy can heat the upper layers of the atmosphere, causing its density to increase. This change can alter the orbits of satellites and even contribute to the accumulation of space debris, further complicating space operations. As humanity's reliance on technology grows, understanding and predicting the impacts of solar flares has become essential for safeguarding not only our infrastructure, but also the long-term stability of our digital world. This continuous research and monitoring have never been more critical. Cosmic events like supernovae, the explosive deaths of massive stars, wield an immense influence on the universe. When a star nears the end of its life, having exhausted its nuclear fuel, it expels its outer layers into space at extraordinary speeds. This explosion releases an overwhelming amount of energy and scatters elements formed in the star's core across the universe. These elements, such as carbon, oxygen, and iron, are the building blocks of life as we know it. In fact, one could argue that without the remnants of ancient supernovae, the rich chemistry that supports life on Earth may never have come into being. When a supernova occurs close enough to Earth, the consequences can be more direct. These cosmic explosions emit intense bursts of radiation, including gamma rays, which could have serious repercussions for our atmosphere. If a supernova were to take place within about 100 light years of Earth, it might severely disrupt the ozone layer, which protects the planet from harmful ultraviolet radiation. Such an event could trigger a range of ecological impacts, from increased mutation rates among living organisms to potential disruptions in climate patterns. Interestingly, some researchers believe that supernovae may have played a role in mass extinction events throughout Earth's history. For example, a series of supernovae active around the time of the Ordovician-Silurian extinction may have contributed to environmental changes that led to dramatic shifts in biodiversity. These cosmic events remind us that the universe is not a silent backdrop to Earth's existence, but an active participant in shaping the planet's history. Through their fiery explosions and the elements they create, supernovae have influenced the course of life on Earth, shaping not only the material that makes up our world, but also the evolutionary path that life has followed over millions of years. Earth's magnetic field plays a crucial role in shielding life on our planet from harmful cosmic radiation. Generated by the movement of molten iron within Earth's outer core, this magnetic field extends far into space, creating a protective cocoon known as the magnetosphere. This invisible shield acts as a barrier between us and the constant bombardment of charged particles emitted by the sun and other cosmic sources. These particles, primarily protons and electrons, travel at extraordinary speeds and, without the magnetic field, would collide with Earth's atmosphere and surface, potentially causing significant damage to living organisms. Such interactions could damage DNA, increase the risk of cancer, and result in a variety of other health issues. In essence, Earth's magnetic field is one of the most critical features that enables life to exist and thrive on our planet. Without it, the harsh forces of the cosmos would relentlessly attack our atmosphere and living organisms, disrupting the delicate balance that sustains life. The magnetic field, like the atmosphere, is a reminder of how interconnected Earth is with the cosmos, providing a shield that ensures our continued survival in the vast, unpredictable expanse of space. However, the magnetosphere plays a crucial role in shielding Earth from the harmful effects of cosmic radiation, deflecting most charged particles away from the surface. This protective magnetic field is essential in preserving the integrity of both our atmosphere and biological systems. One of the most fascinating aspects of Earth's magnetic shield is its dynamic and adaptive nature. Unlike a simple static barrier, the magnetosphere fluctuates in response to changes in solar activity. During significant solar events such as solar flares or coronal mass ejections, the protective capabilities of the magnetic field intensify, or its shape may shift, offering an ever-evolving defense against the incoming solar particles. This responsiveness ensures that while we continue to benefit from cosmic radiation at minimal, harmless levels, we are shielded from the more intense, potentially harmful surges that could arise during solar storms. The more we understand Earth's magnetic field, the clearer it becomes just how integral it is to our existence, not only for protecting our health, but also for highlighting our planet's exceptional position in the vastness of space. Earth's magnetic field creates a sanctuary in which life can flourish, demonstrating the complex and finely tuned balance of natural forces that enable our survival. This protective force is a striking reminder of the delicate equilibrium between various cosmic elements that work in harmony to make life possible here. As we explore deeper into Earth's magnetosphere, we also gain insights into the greater relationship between planetary systems and cosmic phenomena, showcasing just how interconnected the cosmos is with our daily lives. An intriguing connection exists between climatological events on Earth and astronomical phenomena. At the core of this relationship is energy, primarily sourced from the sun. The sun's radiation is a key factor in determining Earth's climate and is continually influenced by various celestial occurrences, such as solar flares and sunspots. Solar flares, which are powerful bursts of energy from the sun, have a direct impact on Earth's atmosphere, causing fluctuations in temperature and weather patterns. In addition to this, solar flares can also disrupt communication systems, satellite operations, and even electrical grids, emphasizing the sun's far-reaching influence. Beyond the sun's impact, other astronomical bodies like the moon also exert their influence on Earth's climate. The moon's gravitational pull is a primary force driving the ocean tides, but its effects extend far beyond that, influencing atmospheric patterns as well. Research has shown that the alignment of the moon and sun can contribute to extreme weather events, such as heavy storms or rainfall. The cyclical nature of the moon's phases can lead to subtle variations in atmospheric pressure, which, over time, can impact the climate. Additionally, the gravitational pull of the moon helps stabilize the tilt of Earth's axis, an essential factor in maintaining a relatively stable climate over long periods. Long-term astronomical cycles, such as the Milankovitch cycles, also play a significant role in shaping Earth's climate. These cycles, which span tens of thousands to hundreds of thousands of years, involve gradual shifts in Earth's orbit and axial tilt. Such changes influence how much solar energy Earth receives, driving significant shifts in climate, including alternating glacial and interglacial periods. Scientists use various methods, such as analyzing sediment cores and ice cores, to study past climate conditions and their correlation with these astronomical cycles. The study of such long-term changes offers valuable insights into how Earth's climate has fluctuated over millennia and how it might continue to evolve in the future. Cosmic events, such as supernovae or changes in the intensity of cosmic rays, could also influence Earth's climate over extended time periods. Cosmic rays, which originate from outside our solar system, interact with Earth's atmosphere and play a role in cloud formation. Variations in the intensity of these cosmic rays may impact weather patterns, though the direct link between such events and short-term climatological changes is still being explored. Nonetheless, this serves as a powerful reminder of how deeply connected Earth is to the broader universe. It highlights the intricate relationship between our planet's atmospheric conditions and the celestial phenomena that occur light years away, emphasizing the delicate balance that sustains life on Earth. Throughout history, ancient cultures have left behind remarkable geoglyphs, large-scale designs etched into the Earth's surface, which offer intriguing insights into the ways they perceived and interacted with celestial events. These monumental artworks were often created with profound intentions tied to their understanding of the cosmos. For many ancient societies, the movement of the stars, planets, and other celestial bodies was not just a distant phenomenon, but an integral part of their daily lives. The heavens were seen as deeply intertwined with agricultural practices, spiritual beliefs, and the broader understanding of time. Take, for example, the mysterious Nazca lines in Peru. These geoglyphs have been the subject of much study, and it is clear that many of the figures align with significant solar and lunar events. Some of the lines are carefully positioned to point toward the sunrise during the summer solstice or the sunset during the winter solstice, suggesting a deliberate design aimed at tracking these celestial occurrences. This alignment of the geoglyphs with key astronomical events indicates a sophisticated knowledge of the sky. These ancient creators were not only skilled artists, but also keen observers of the natural world, integrating their celestial observations into their cultural and spiritual expressions. The significance of these alignments transcends mere aesthetic choices. The placement of a geoglyph in relation to a celestial event could serve as a marker for agricultural activities, signaling the optimal times for planting or harvesting crops. This highlights the profound connection between the ancient people's understanding of the cosmos and their daily existence. Through these monumental structures, they expressed both practical and symbolic knowledge, forging a lasting bond between the earth and the heavens. Even today, archaeologists and astronomers continue to explore the significance of these ancient alignments, revealing a rich tapestry of human knowledge and experience in relation to the cosmos. The moon plays an indispensable role in stabilizing Earth's climate and environment, primarily through its gravitational influence. This relationship has far-reaching effects on the planet's axial tilt, which is tilted at an angle of approximately 23 degrees. This tilt is crucial as it determines how sunlight is distributed across the globe, creating the seasons we experience. Without the moon's stabilizing influence, Earth's axial tilt could vary significantly over time, leading to extreme fluctuations in climate, potentially making Earth far less hospitable to life. Thus, The moon's gravitational pull not only influences the tides, but also plays a key role in ensuring the long-term stability of Earth's climate, reinforcing the delicate balance required for life to thrive. As the moon orbits Earth, its gravitational pull exerts a powerful force, generating bulges of water across the planet's oceans. These bulges are what create the ebb and flow of tides, a natural rhythm that shapes the very dynamics of Earth's coastlines. Tides, though often viewed as mere curiosities, are far more than a spectacle of nature. They are crucial players in maintaining the delicate balance of coastal ecosystems. The movement of water not only influences the physical landscape, but also nurtures the diverse habitats that support marine life. As the tides rise and fall, they help circulate vital nutrients, ensuring that plankton, fish, and other marine organisms thrive in their habitats. This cyclical process sustains biodiversity, a cornerstone for life under the sea. The moon's impact stretches beyond the water's edge, however. Its gravitational pull also extends to Earth's atmosphere, subtly influencing wind patterns and atmospheric circulation. These shifts, in turn, contribute to the planet's overall climate stability. Working in harmony with the energy we receive from the sun and Earth's own rotation, the moon plays a vital role in shaping the conditions that make life on Earth possible. Without the moon, our planet would likely experience a much more volatile environment, one that may not have supported the diverse ecosystems and weather systems we see today. Thus, though the moon may seem like a passive observer in the night sky, its constant gravitational dance with Earth is actively securing a more stable, flourishing world. Turning our gaze beyond Earth, the field of astrobiology opens up a new window into understanding not only the origins of life on our own planet, but also the potential for life on distant worlds. By studying life in the universe, scientists gain a deeper understanding of the unique conditions that made life possible on Earth and how these conditions have shaped the planet's evolution over billions of years. One of the most intriguing aspects of astrobiology lies in the discovery of extremophiles, organisms that thrive in the most extreme environments on Earth, such as the high-pressure depths of deep sea, hydrothermal vents, or the freezing, desolate expanses of the polar tundras. These organisms offer a glimpse into the resilience of life, suggesting that the very first forms of life on Earth may have emerged under similarly harsh and inhospitable conditions. Astrobiology not only provides clues about the adaptability of life, but also guides our exploration of other planets. By comparing geological and atmospheric conditions across different worlds, scientists are able to determine which planets might be capable of sustaining life. The study of Mars, for instance, and the icy moons of Jupiter and Saturn provides valuable insights into the processes that could have allowed life to emerge, or might still allow it to emerge, on other worlds. Discoveries such as the identification of organic molecules or signs of ancient water on these celestial bodies deepen our understanding of Earth's own origins and its potential to harbor life in the future. Another compelling aspect of astrobiology is the exploration of Earth's biosphere and its profound influence on our planet's atmospheric and geological conditions. Tracing the major events that have shaped Earth's climate and its living organisms over time, such as the Great Oxygenation Event, helps us understand the interconnection between life and its environment. During the Great Oxygenation Event, cyanobacteria began producing oxygen, drastically transforming the Earth's atmosphere and paving the way for the rise of more complex life forms. This process parallels the search for biosignatures on exoplanets as scientists attempt to identify potential markers of life on distant planets. By examining these processes, we gain a broader perspective on how life might emerge elsewhere in the galaxy. The fundamental biochemical processes that allow life to thrive are also central to the study of astrobiology. By understanding how organisms interact with and alter their environment, scientists can identify the conditions that are most conducive to life. This knowledge does more than inform our search for life beyond Earth. It also helps us better understand the ongoing evolution of life on our planet. Through this lens, we see that life on Earth is not a singular, isolated phenomenon, but part of a vast, interconnected network of cosmic processes that enable the existence of life in the universe. One of the most fascinating sources of information about Earth's history is found in its ice cores. cylindrical samples drilled from glaciers and ice sheets. These cores act as time capsules, preserving an archive of Earth's climate history. Within these frozen layers, scientists have uncovered gases, dust particles, and isotopes that tell the story of the planet's past atmospheric conditions. Of particular interest are elements and compounds that hint at cosmic impacts, such as those from asteroids or comets. These events have left traces in the ice, with certain isotopes, such as iridium or osmium, appearing in layers that correspond to known impact events. Research into these isotopes provides a compelling link to Earth's history of mass extinction events. The dramatic effects of a significant cosmic impact, like the one believed to have contributed to the extinction of the dinosaurs, are preserved in these ice cores. After such an impact, dust and debris would scatter across the globe, increasing the concentration of these isotopes. These microscopic particles, including soot and glass formed by the heat of the collision, provide a tangible record of catastrophic events that reshaped life on Earth. The study of ice cores thus offers an invaluable opportunity to examine the profound effects cosmic forces have had on Earth's climate, geology, and biological history. Finally, Earth's seasons, long understood through the tilt of its axis and its orbit around the Sun, are further influenced by solar activity. The Sun is not a static entity, but is constantly undergoing changes, including phenomena like sunspots, solar flares, and coronal mass ejections. These shifts in solar output can have a profound effect on Earth's atmosphere, leading to fluctuations in climate and seasonal patterns. During periods of heightened solar activity, increased radiation can warm certain regions, especially those directly exposed to the Sun's rays. As such, the Sun's energy plays a significant role in modulating Earth's climate, contributing to the intricate interplay of factors that make life on our planet possible. In essence, the interconnectedness of cosmic, atmospheric, and biological processes creates a dynamic and finely tuned system that has sustained life on Earth for billions of years. Whether through the moon's influence on our tides, the exploration of life's potential on distant worlds, or the study of cosmic impacts recorded in ice, each element provides a crucial piece to the puzzle of how life flourishes. By continuing to explore and understand these intricate relationships, we gain a deeper appreciation for the delicate balance that sustains life on Earth, and perhaps even on other planets across the universe. Conversely, periods of reduced solar activity can be linked to cooler temperatures on Earth, which could also lead to more severe winters. This relationship, however, becomes increasingly intricate when considering the cyclical nature of solar activity, which typically follows an approximately 11-year pattern. Scientists have closely monitored these solar cycles, observing that they can bring about distinct changes in global weather patterns. Despite these observations, the exact mechanisms behind these shifts remain an area of ongoing research and exploration. One of the most intriguing aspects of this connection is understanding how variations in solar activity not only influence global temperatures, but also shape extreme weather events. Some researchers hypothesize that the Sun's magnetic field may play a pivotal role in affecting the jet stream, a powerful air current that governs weather patterns across the planet. This influence could potentially alter the course of storms, droughts, and other extreme weather phenomena. As the Earth's climate system is multifaceted, this raises an essential question. How much of the Earth's changing climate is intrinsically tied to solar cycles, and how much is driven by human-induced factors like greenhouse gases or ocean currents? Unraveling this complex web of natural and anthropogenic factors is crucial in the context of the rapidly changing climate. As humans continue to modify the atmosphere through industrial emissions and other activities, scientists are eager to understand how these alterations might interact with the natural rhythms of solar activity. This research is not just about understanding annual weather patterns, but about developing a robust framework for predicting long-term climate trends and potential climate disasters. As extreme weather events grow more frequent and intense, such insights will be vital in preparing for, mitigating, and adapting to the challenges posed by these changes. Looking forward, the future of space exploration promises even greater discoveries, with numerous ambitious missions poised to expand our knowledge of distant planets within our solar system and beyond. Among the most highly anticipated is the Mars Sample Return mission, a collaborative effort between NASA and the European Space Agency. This mission aims to retrieve soil and rock samples from the Martian surface and return them to Earth for detailed analysis. The primary goal of this mission is to unlock clues about Mars's history, including its potential to support life in the distant past. By analyzing these samples, scientists hope to answer long-standing questions about the red planet's habitability. Equally significant is the Europa Clipper mission, slated for launch in the near future. This mission will focus on Jupiter's moon, Europa, which is believed to harbor a vast subsurface ocean beneath its frozen exterior. Scientists are particularly intrigued by the possibility that Europa's ocean might contain the essential ingredients for life, as we understand it. Equipped with a sophisticated suite of instruments, Europa Clipper will study the moon's atmosphere, surface composition, and internal structure, providing critical insights into the conditions that may support life on this enigmatic world. Meanwhile, the Dragonfly mission to Titan, Saturn's largest moon, is set to embark on its journey in 2027. This mission will feature a unique rotorcraft designed to explore Titan's alien surface in a way that no previous mission has attempted. Titan's landscape, dotted with lakes of liquid methane and ethane, presents an entirely new type of environment for scientific investigation. The Dragonfly team hopes to uncover clues about prebiotic chemistry, processes that could resemble those that took place on Earth billions of years ago, potentially shedding light on the origins of life itself. In addition to these planetary missions, the James Webb Space Telescope, JWST, is set to revolutionize our understanding of distant exoplanets. While not a planetary exploration mission in the traditional sense, JWST will analyze the atmospheres of exoplanets orbiting distant stars. By collecting light from these far-off worlds, the telescope aims to identify chemical signatures that could point to the presence of life-sustaining elements, such as water or organic molecules. This mission holds the potential to reshape our understanding of habitability in the universe, challenging our assumptions about life beyond Earth. The next decade of space exploration promises to be an exhilarating chapter in humanity's quest for knowledge. At the heart of this exploration is the Artemis program, led by NASA, with the bold vision of establishing a sustainable human presence on the moon by the end of this decade. Central to this mission is the development of advanced technologies and infrastructure capable of supporting long-term human habitation on the lunar surface. Artemis aims not just to visit the moon, but to create a permanent base that will facilitate ongoing scientific research and exploration. One of the key components of the Artemis mission is the Lunar Gateway, a space station designed to orbit the moon. This gateway will serve as a staging point for astronauts traveling to and from the lunar surface, acting as a hub for various operations and missions. It will enable astronauts to carry out scientific experiments, build infrastructure, and even perform repairs using resources extracted directly from the moon's surface, greatly reducing the need for supplies to be sent from Earth. This ambitious project promises to lay the groundwork for humanity's next steps into deep space, offering new opportunities for discovery and growth. The program places a significant emphasis on the concept of in situ resource utilization, ISRU, a strategy designed to make use of the natural resources available in space. One of the most exciting prospects of this approach is the potential for harnessing water ice, which may be found in the permanently shadowed craters of the moon. This ice could be converted into vital resources like oxygen and hydrogen. Oxygen is essential for astronauts' survival, while hydrogen can be used as a fuel for rockets. This capability opens up a new frontier in space exploration, enabling missions to extend their duration and reach further than ever before. By utilizing the moon's natural resources, humans can establish a sustainable presence on the lunar surface, enhancing our capacity for continued exploration of the moon and beyond. The Artemis program is not just about sending astronauts back to the moon. It is laying the groundwork for more ambitious missions, including future expeditions to Mars. The lessons learned from establishing a sustainable base on the moon will be critical for planning future human missions to other planets and moons. This could mark a pivotal moment in humanity's journey to become a spacefaring civilization, unlocking possibilities that were once considered beyond reach. Among the most promising areas of development in deep space exploration is the advancement of next-generation propulsion systems. Traditional rocket engines, while effective, are reaching the limits of their capabilities. As the scope of space missions expands, innovative propulsion technologies are being explored. One such solution is ion propulsion, which works by using electric fields to accelerate ions, generating thrust. This technology offers remarkable efficiency, allowing spacecraft to travel faster and use far less fuel. The potential to reach distant planets more quickly, thus reducing travel time, could revolutionize space exploration. Alongside these propulsion advancements, robotic spacecraft are evolving at an astonishing pace. New autonomous drones, powered by artificial intelligence, are being designed to carry out both exploration and complex analysis on distant worlds. These drones can make real-time decisions, navigating hazardous terrains and performing scientific tasks without the need for human intervention. This autonomy is indispensable for missions in deep space, where communication delays make real-time interaction with Earth impossible. In addition to propulsion and robotics, advancements in communication technologies are reshaping the landscape of deep space exploration. As we venture farther into the cosmos, conventional radio waves become less effective for transmitting vast amounts of data. Laser communication systems, which use light to transmit information instead of radio waves, represent a quantum leap forward. These systems could provide high-speed data transfer, allowing scientists to receive high-resolution images and valuable data from distant missions almost instantly, despite the vast distances between Earth and the spacecraft. Power generation and storage technologies are also advancing rapidly. As missions travel farther from the sun, conventional solar panels become less effective due to the decreasing amount of sunlight. To address this, new power systems are being developed, such as compact nuclear reactors and radioisotope thermoelectric generators. These systems are designed to provide a steady, reliable energy source that can last for decades, ensuring that spacecraft can continue to operate and conduct experiments without interruption, regardless of their distance from the sun. With these technological advancements, humanity is expanding its reach into the universe, unlocking mysteries that were once unfathomable. Missions to Mars, in particular, hold the potential to revolutionize our understanding of life and the conditions necessary for habitability. Mars, often referred to as Earth's twin, offers a unique opportunity to explore the ancient history of water on another planet. Evidence suggests that billions of years ago, Mars may have had rivers, lakes, and perhaps even oceans. By studying the sedimentary deposits and geological formations on Mars, scientists aim to reconstruct the environmental conditions that may have existed when water was abundant on the planet's surface. This could provide crucial insights into whether Mars ever supported life. The search for microbial life is at the forefront of these Mars missions. Robotic landers and rovers equipped with state-of-the-art scientific instruments are designed to analyze the Martian soil and rocks for organic compounds and biosignatures, key indicators of past or present life. If any trace of life is found, it would not only confirm that life can exist beyond Earth, but would also challenge our understanding of how life begins and thrives in diverse environments. These findings could lead to new hypotheses about the origins of life and what conditions are necessary for its existence. Astrobiology, the study of life in extreme environments, plays a crucial role in these Mars missions. By examining the Martian climate and its ability to support life, scientists are refining the criteria that will guide the search for habitability on other planets and moons, particularly exoplanets orbiting distant stars. If Mars, with its harsh and inhospitable conditions, once supported life, it suggests that other seemingly barren worlds might also harbor life beneath their surfaces. This could fundamentally change our search parameters and expand the list of celestial bodies worthy of exploration. As these missions progress, they will not only increase our understanding of Mars, but also set the stage for future explorations of other planets and moons. The techniques and methodologies developed during these missions could be applied to icy moons, distant planets, and even exoplanets, deepening our quest to determine whether life exists beyond Earth. Each new discovery on Mars could serve as a stepping stone in this ongoing search, echoing across the cosmos as we strive to understand whether life is a universal phenomenon. Planning crewed missions to the outer planets introduces a host of challenges that stretch the capabilities of current space exploration technologies. One of the primary obstacles is the vast distances involved. For instance, a mission to Jupiter or Saturn would take several years to complete, requiring astronauts to spend extended periods of time in a confined spacecraft. This raises significant questions about the mental and physical health of the crew, as well as the social dynamics of life in such an isolated environment. As the spacecraft travels farther from the Sun, it must also contend with extreme environmental conditions. The temperatures become much colder, and radiation levels from cosmic sources increase, posing a threat to the health and safety of the crew. Developing effective shielding against this radiation is crucial, as prolonged exposure could lead to severe health issues such as cancer or neurological damage. Protecting astronauts from these hazards is a priority for mission planners. Furthermore, life support systems for such long-duration missions need to be autonomous and reliable. Given the enormous distance from Earth, resupply missions would be impractical. Therefore, life support systems must be capable of recycling air, water, and waste, while also providing astronauts with the means to grow food and maintain their health for several years without external assistance. Research into closed-loop life support systems is ongoing, but it remains a significant challenge to ensure these systems can function effectively over long periods. Finally, the technological hurdles associated with propulsion, navigation, and communication systems must be addressed. Traditional propulsion systems are not efficient enough to make the extended travel time and distance involved in these missions feasible. As a result, scientists are exploring alternatives such as nuclear propulsion and solar sails. While these technologies show great promise, they remain in the developmental phase and have yet to be fully realized. Despite the significant challenges, each step forward in these areas of research brings humanity closer to the goal of exploring the outer reaches of our solar system and beyond. As humanity ventures deeper into the cosmos, the challenges of maintaining communication with Earth become increasingly complex. The further we travel, the more difficult it becomes to relay information back to our home planet. This growing distance necessitates the development of highly sophisticated systems capable of overcoming the significant delays inherent in signal transmission. To ensure that these challenges are met and overcome cohesively, we must continue to innovate and refine technologies. Only through such advancements can we pave the way for the successful exploration of the outermost reaches of our solar system. One of the most significant shifts in space exploration has come from private space companies, which have rapidly become key players in expanding our capabilities. These companies, by introducing innovative technologies and strategies, have dramatically enhanced the pace and scope of our ventures into space. They've opened up new opportunities for exploration by reducing the high costs traditionally associated with space missions and by creating more accessible pathways to space. Their work is also accelerating the development of scientific missions that were previously either too expensive or too complex to undertake. Leading the charge are companies like SpaceX, Blue Origin, and Virgin Galactic, all of which have revolutionized space travel through the development of reusable rocket technologies. This breakthrough innovation has made a profound difference by slashing the costs of launching payloads into orbit. Reusable rockets are now able to take off, land, and be used multiple times, dramatically reducing the financial burden of space exploration. In doing so, these companies have made it possible for more scientific research missions to take place, which in turn brings us closer to unlocking the mysteries of our universe. But the contributions of private space firms go beyond just the development of technology. Their ability to foster collaboration with government agencies like NASA has been a game changer. By partnering with private companies, NASA and other governmental space agencies can now complete missions that would have once been financially prohibitive or logistically insurmountable on their own. Through contracts for resupply missions to the International Space Station, ISS, private firms are playing an essential role in sustaining long-term research on the station, while simultaneously advancing their own technological capabilities in preparation for future exploration. This synergy between public and private sectors is a vital component in the continued growth of space exploration. It creates a robust foundation for the advancement of scientific knowledge, while also building a stronger presence in space that will ensure we remain on the cutting edge of discovery. Private space firms are also setting their sights beyond low Earth orbit, with the Moon and Mars now squarely on their radar. SpaceX's ambitious plans, for example, include not only sending astronauts to Mars, but also establishing a long-term sustainable human presence on the planet. This bold vision is designed to inspire a new generation of scientists, engineers, and explorers, all of whom will be crucial in pushing the boundaries of space exploration. The possibility of colonizing Mars, coupled with other groundbreaking missions, has sparked renewed enthusiasm for space, drawing talented individuals from diverse fields to contribute to these transformative projects. The growing influence of private companies in space exploration has also triggered a wave of innovation in the development of small satellite technologies. These smaller, more cost-effective satellites are playing an increasingly crucial role in monitoring Earth's environment, studying climate change, and enhancing global telecommunications. By experimenting with new methods of deploying these small satellites, private space companies are expanding our ability to observe both our planet and the vast reaches of the cosmos, all while making it more affordable and efficient to do so. The introduction of private industry into space exploration has brought a dynamic energy that is transforming our understanding of the universe. One area where these efforts are particularly impactful is in the exploration of the gas giants and their moons, such as Jupiter and Saturn. These two massive planets are surrounded by numerous moons, many of which hold tantalizing secrets that could reshape our understanding of life beyond Earth. One of the most intriguing of these moons is Europa, one of Jupiter's largest satellites. Beneath its thick, icy crust, scientists believe there may be a global ocean of liquid water, a discovery that dramatically increases the potential for life in such an environment. Researchers are particularly curious about the possibility of extremophiles, organisms that thrive in Earth's deep, frigid oceans, existing beneath Europa's surface. Further adding to the mystery is Ganymede, another of Jupiter's moons. Ganymede is particularly unique because it is the only moon in our solar system known to have its own magnetic field. This magnetic field raises fascinating questions about the moon's internal structure and how its ocean might interact with its environment. These revelations open new avenues of research and may even provide critical insights into the moon's geological history, as well as its potential to harbor life. Saturn's moons, particularly Enceladus and Titan, are equally captivating. Enceladus, for instance, is known for its geysers, jets of water vapor and ice particles that erupt into space from its surface. This phenomenon suggests that the moon may have a complex and active interior, one that could harbor a subsurface ocean. The discovery of organic molecules in these plumes has only heightened the excitement about the possibility of life beneath Enceladus's icy shell. Titan, Saturn's largest moon, presents a completely different set of mysteries. Unlike Earth, Titan's thick atmosphere and its lakes made of methane and ethane create a vastly different chemistry, one that could open the door to the discovery of alternative forms of life. The possibility of life existing in such an exotic environment challenges everything we think we know about the conditions required for life to thrive. As our understanding of these moons grows, so too does the anticipation surrounding future missions to explore them. The idea of life in such strange alien environments has the potential to completely transform our view of the cosmos and humanity's place within it. These moons, so far removed from our terrestrial experience, are poised to provide us with an unprecedented opportunity to revolutionize our understanding of life in the universe and the processes that govern the evolution of water worlds. Beyond our solar system, future advancements in telescope technology hold the promise of transforming our understanding of distant galaxies. New telescopes equipped with larger mirrors and more powerful detectors will allow astronomers to peer deeper into the cosmos than ever before. These innovations will enable us to capture light from galaxies that are billions of light years away, revealing details that are currently beyond our reach. Additionally, the incorporation of advanced technologies like adaptive optics will improve image clarity, allowing us to compensate for atmospheric distortion and improve the precision of ground-based observations. As a result, future telescopes will provide sharper, more detailed images, that offering scientists unprecedented insights into the structures and compositions of distant galaxies, and ultimately allowing us to probe deeper into the mysteries of the universe. The relentless march of scientific progress in the fields of infrared and radio wavelengths is poised to transform our understanding of the cosmos. These advancements open the door to the exploration of celestial phenomena that remain hidden from the view of traditional visible light telescopes. Objects like cooler stars, distant nebulas, and other enigmatic celestial bodies, which play crucial roles in the formation of stars and galaxies, can now be studied in unprecedented detail. The ability to observe these phenomena at wavelengths beyond what the human eye can detect is a pivotal leap in cosmic discovery. Moreover, the next generation of telescopes will be equipped with the ability to survey the entire sky, offering a panoramic view of the universe like never before. This capacity will not only allow for more thorough investigations into the populations of galaxies, but also enable scientists to gather vast amounts of data in significantly shorter timeframes. With the power to map the distribution of galaxies across the vast expanse of space, researchers will unlock insights into the fundamental processes that drive galaxy evolution, shedding light on the dynamics of cosmic formation and interaction. These telescopes, with their far-reaching capabilities, will help paint a clearer picture of the universe's past, present, and future. As these groundbreaking observations flood in, the challenges of analyzing such enormous amounts of data will become more pressing. Here, cutting-edge digital processing and sophisticated machine learning algorithms are set to play a crucial role. By sifting through complex data, these tools can help identify hidden patterns, correlations, and connections, providing a clearer understanding of the intricate events that have shaped our cosmic history. This fusion of technology and astronomy is not just making discoveries more frequent, it is making them more profound, as it allows for deeper dives into the mysteries that lie at the very fabric of the universe. Looking forward, we stand on the brink of a new era in space exploration, largely fueled by monumental advancements in telescope technology. Instruments like the James Webb Space Telescope, alongside its future successors, are expected to lead the charge in unraveling the most fundamental questions about the universe. These instruments promise to answer profound inquiries regarding the origins of galaxies, the existence of life beyond Earth, and the very structure of the cosmos itself. As these missions progress, they will reveal a universe brimming with mysteries, offering glimpses into realms previously thought beyond our reach. But these extraordinary advancements do not happen in isolation. They are the result of collaborative efforts from researchers and scientists around the globe, whose collective endeavors continue to push the boundaries of space science. International partnerships have become the backbone of these breakthroughs, enabling countries to pool their resources, expertise, and technologies. This global cooperation fosters a spirit of unity, with each nation contributing to a shared vision of expanding our understanding of the universe. One of the most notable examples of such collaboration is the International Space Station, ISS, where scientists from across the world work side by side to conduct experiments in microgravity. These experiments provide invaluable data about how physical phenomena behave in space, helping researchers understand everything from human biology to the fundamental laws of physics. But the ISS is just one facet of a far-reaching network of international research collaborations. The Event Horizon Telescope, a monumental project that produced the first ever image of a black hole in 2019, exemplifies the power of global cooperation. This achievement was the result of a massive joint effort, with scientists from various countries analyzing data collected from a network of radio telescopes scattered across the globe. Similarly, the European Southern Observatory, ESO, in Chile stands as a beacon of international collaboration. providing astronomers from multiple countries access to some of the best dark sky conditions on Earth. The ESO has been pivotal in advancing our understanding of the universe. These kinds of partnerships not only allow for the pooling of resources and expertise, but also help mitigate the substantial costs associated with large-scale space projects, like the development of next-generation telescopes and interplanetary missions. International cooperation also facilitates the exchange of knowledge, expertise, and cultural understanding. Scientists working across borders bring diverse perspectives to the table, creating an environment where innovation can flourish. The cross-pollination of ideas often leads to breakthroughs that no single nation could achieve alone. As we look toward the future, the importance of continued collaboration in cosmic research cannot be overstated. With the universe as vast and complex as it is, only through collective effort can we hope to unravel its mysteries. Simultaneously, the field of space travel is undergoing a profound transformation. Propulsion technology, long constrained by the limitations of chemical rocket engines, is advancing at a rapid pace. While traditional rockets work on the principle of expelling mass to generate thrust, they face significant limitations when it comes to long-duration space missions. These chemical engines, though effective for launching payloads to low Earth orbit, struggle with the inefficiencies required for deep space exploration. As a result, new propulsion technologies are being developed that could change the very nature of space travel. Ion propulsion systems, for instance, offer a promising alternative to chemical rockets. By using electric fields to accelerate ions, these systems can generate a much more efficient thrust, allowing spacecraft to travel farther and faster with less fuel. Missions like NASA's Dawn spacecraft have demonstrated the effectiveness of ion propulsion as it explored distant asteroids, providing valuable data about the early solar system. This technology holds the potential to drastically reduce travel times to distant planets and moons, bringing them within reach for exploration. Equally intriguing is the concept of solar sails. These large, reflective surfaces harness the pressure of sunlight itself to propel spacecraft through space. By catching photons from the sun, solar sails can gradually accelerate a spacecraft without the need for traditional fuel. This opens up the possibility for deep space exploration missions that require minimal resources, enabling us to venture to distant corners of the solar system and beyond. With ongoing advancements in material science, solar sails are becoming increasingly viable, making the dream of exploring far-flung regions of space more attainable than ever before. These advancements in propulsion technology are not just changing the way we explore our own solar system, they are also bringing the prospect of interstellar travel closer to reality. Once confined to the realm of science fiction, the idea of traveling to other star systems is now being taken seriously, thanks to innovations in propulsion. As technology continues to evolve, humanity may one day stand at the threshold of exploring not just other planets, but entirely new stars and even potentially habitable exoplanets. At the core of all these discoveries lies a profound shift in our understanding of time and existence. The study of the cosmos is forcing us to rethink what we know about the very nature of reality. Through the theory of general relativity developed by Albert Einstein, scientists have come to understand that time is not a fixed, immutable entity, but something that is deeply connected to the fabric of space itself. In regions of strong gravitational fields, like those near a black hole, time can stretch and bend, leading to the phenomenon known as time dilation. This means that time flows differently depending on the strength of the gravitational forces acting upon it. For example, time would pass much more slowly for someone near a black hole compared to someone far away from its gravitational influence. These revelations about time challenge our fundamental understanding of reality, offering us a new lens through which to view the universe. As we continue to explore the cosmos, we are not only uncovering the secrets of distant stars and galaxies, but also redefining the very nature of existence itself. Our journey into the cosmos has unveiled an astonishing revelation. Time, like the universe itself, may have both a beginning and potentially an end. The Big Bang Theory, a cornerstone of modern cosmology, suggests that roughly 13.8 billion years ago, our universe emerged from an extremely hot and dense state. This event did not merely mark the birth of space, but also heralded the beginning of time as we understand it. As we peer deeper into the origins of the universe, our investigations lead us to the cosmic microwave background radiation, a faint echo of the early universe, which offers a glimpse into the conditions that prevailed in the primordial moments after the Big Bang. This allows us to place our existence within a temporal framework, urging us to consider not only where we are, but also when we are. As we observe the universe expanding, a sense of awe and curiosity arises, prompting us to question the future of the cosmos and, by extension, the fate of time itself. Some cosmologists speculate on what is known as the heat death of the universe, a scenario in which the universe, after an infinite amount of time, reaches a state of maximum entropy. In this far distant future, all energy would be evenly distributed and stars would burn out, leaving behind a universe that is cold, dark, and devoid of any usable energy. This concept underscores the delicate relationship between our understanding of existence and the ever-evolving nature of the cosmos. The realization that time itself could have an end highlights the transient nature of our own lives, nestled within an ever-expanding universe that will one day fade into stillness. Moreover, our cosmic perspective offers an opportunity to reflect on our place in this magnificent universe. It is a humbling thought that we are all, in essence, made of star stuff, the remnants of stars that exploded in supernovae, spreading their elements across the universe. In understanding the grand cycles of creation and destruction in the cosmos, we begin to appreciate our own fleeting existence as part of a much larger, continuously unfolding cosmic narrative. This realization not only deepens our comprehension of the universe's physical laws, but also instills in us a profound sense of our transitory nature within the grand timeline of an ancient and ever-evolving story. The discovery of extraterrestrial life introduces a series of profound ethical questions that challenge our understanding of existence, identity, and responsibility. Among the foremost questions is one of rights. If we were to make contact with alien beings, what rights would they possess? This inquiry pushes us to reconsider the ethical frameworks we apply to life in general, expanding our perspective beyond Earth-centric views to encompass the potential complexities of alien life forms. It forces us to reconsider not only the moral status of other forms of life, but also our role as stewards of both Earth and any extraterrestrial entities we might encounter. Scientific exploration at the heart of this ethical debate drives humanity's quest for knowledge, but also brings with it immense responsibility. The pursuit of knowledge, though noble, carries the potential for exploitation or harm if handled recklessly. Just as we debate the ethics of animal rights and environmental conservation on Earth, so too must we tread carefully when engaging with any life forms beyond our planet. We must be vigilant not to repeat the historical mistakes of colonization and ecological disregard. Such considerations force us to reflect on the ways in which our scientific endeavors might impact the very beings we aim to understand. The philosophical ramifications of encountering extraterrestrial life are equally profound. Such a discovery could shatter long-held beliefs about human exceptionalism, individuality, and spirituality. Our place in the universe, once thought to be singular and unique, would no longer be so certain. Psychologically and sociologically, humanity would face a massive reckoning, reconciling our identity in a universe that might not be as solitary as we once believed. These existential questions demand open dialogue among scientists, ethicists, and the broader public, allowing for the development of ethical guidelines and frameworks that are inclusive of diverse perspectives. Such a collective approach could help ensure that any engagement with extraterrestrial life is governed by respect, caution, and an unwavering commitment to dignity and coexistence. Looking forward, the exploration of space holds the potential to dramatically reshape not only humanity's future, but also its underlying philosophical outlook. As we venture deeper into the cosmos, we are bound to confront profound questions about life, existence, and our place in the vastness of the universe. For example, the discovery of microbial life on another planet would challenge the long-standing belief that Earth is the only cradle of life. Such a revelation could fundamentally alter our understanding of life's origin and nature, pushing us to rethink our assumptions about what constitutes life and where it can thrive. In addition to expanding our understanding of life, the technologies developed for interstellar travel and habitation could have far-reaching implications for life on Earth. The challenges of space exploration may lead to breakthroughs in energy efficiency, sustainable living, and material science, innovations that could benefit life on our home planet. These advances could not only help us navigate the complexities of space, but also offer solutions to some of Earth's most pressing issues, such as climate change and resource depletion. As humanity reaches out to the stars, the lessons learned from these endeavors could foster a renewed sense of responsibility and stewardship toward Earth and its fragile resources. Moreover, the pursuit of space exploration could serve as a powerful unifying force, encouraging global cooperation and transcending the divisions that often define our world. The challenges of space missions, be they technological, environmental, or political, may inspire us to view ourselves as part of a single human family. As we work together toward common goals beyond our home planet, the barriers that separate us, whether national, cultural, or ideological, may seem less important. This shift in perspective could lead to a new era of peace, where collaboration becomes the norm and the philosophical focus turns to collective progress and mutual benefit. In this sense, space exploration may not only expand our horizons, but also expand the very boundaries of our human identity, encouraging a sense of unity that is essential for facing the challenges of both the cosmos and our planet. The prospect of colonizing other planets ignites a series of ethical debates, drawing a line between the noble ambitions of exploration and the potential exploitation of new worlds. As humanity extends its reach beyond Earth, questions about ownership, environmental sustainability, and the rights of extraterrestrial life become central to the discussion. These questions, framed within a philosophical dialogue, force us to rethink the structures that govern our society. The implications of such a new frontier do not merely challenge our technological capabilities, but could reshape the very moral compass that guides humanity's progress into this vast unknown. Thus, the journey into space becomes more than just an ambitious leap into the cosmic void. It symbolizes a transformative voyage, one that has the potential to redefine not only our understanding of the universe, but also our place within it. As we look outward, we are compelled to confront our collective identity and the very essence of what it means to be human. This exploration of space challenges us to reconsider our priorities, reshape our values, and perhaps, in the process, redefine our future. When we contemplate the sheer vastness of the universe, a multitude of psychological effects often follows. The vastness of space can evoke a sense of awe, wonder, and even humility. The mind struggles to comprehend the true scale of the cosmos, billions of galaxies, each containing billions of stars and planets. In the face of such immensity, it is impossible not to feel small, a speck within the infinite expanse. For many, this realization leads to a profound shift in perspective, igniting a deep desire to understand not just the universe, but the intricate web of connections that bind all life. Yet this sense of awe is not without its darker counterpart. The boundlessness of the universe can also give rise to existential anxiety. The realization that the cosmos is limitless and indifferent can leave one questioning the meaning of existence, the purpose of life, and humanity's role within this cold, unfeeling universe. This confrontation with infinity often drives individuals to reflect on the significance of their own lives. It may inspire some to seek solace in spirituality, others in community, as they struggle with questions that have no easy answers. The weight of such realization can foster a sense of helplessness, yet it also stirs a deep desire for understanding, for finding one's place in a universe so grand and unknowable. On the other hand, the contemplation of the cosmos can also fuel curiosity and a desire for exploration. The mysteries of dark matter, black holes, and the evolution of the universe captivate the imagination. This curiosity drives scientific inquiry, turning what may initially be feelings of anxiety into excitement and anticipation. As people engage with the mysteries of space, the pursuit of knowledge often becomes an antidote to existential dread, offering a sense of connection to something far larger than the individual. This engagement with the universe, far from diminishing the value of life on Earth, can deepen one's appreciation for it. When one understands the fragility of our planet amidst the vastness of space, a sense of responsibility toward the environment and each other emerges. The realization that our home is but a fragile speck in an immense universe can inspire a renewed commitment to preserving the planet, forging a deeper connection with nature and with fellow human beings. It is a reminder that, despite our many differences, we share a common home in the uncharted expanses of the universe. The discoveries made across the cosmos not only challenge our understanding of the universe, but also invite new perspectives on religion and spirituality. As humanity delves deeper into space, we uncover truths about the origins of the universe, the nature of reality, and our place in the grand tapestry of existence. For many, these revelations prompt profound questions about the purpose of life, the design of the cosmos, and the existence of a creator. The idea that the universe began with the Big Bang, for instance, challenges traditional creation narratives found in religious texts. While some see this as a contradiction to their beliefs, others find that the scientific explanation for the universe's origins enriches their understanding of creation, allowing for a more nuanced view of their faith. The vastness of space and the recognition of humanity's smallness within it can provoke profound reflections on spirituality, raising new questions about the nature of the divine and the possibility of a creator who may have orchestrated the cosmos with intention or chance. The search for extraterrestrial life further amplifies these spiritual inquiries. The discovery of life beyond Earth would undoubtedly provoke new theological reflections, challenging our understanding of the divine and how it manifests across different forms of existence. This idea that life may exist in many forms across the universe may suggest that we are all part of a grand cosmic design, a tapestry of life that extends far beyond Earth, possibly woven with intention or the randomness of chance. In this context, science and spirituality are not at odds, rather they converge, each offering unique insights into the nature of existence and the cosmos. However, the intersection of science and spirituality is not without tension. Scientific advancements, particularly those that challenge long-held religious beliefs, can lead to crises of faith for some individuals. As the mysteries of the universe are uncovered, whether through quantum mechanics or the vastness of cosmic evolution, the implications may clash with traditional interpretations of sacred texts. Yet, even in the face of these challenges, many believers find ways to reconcile their faith with new scientific findings. This dynamic interaction between science and religion fosters a dialogue that continues to evolve with each new discovery, as both seek to unravel the mysteries of existence. The potential implications of groundbreaking discoveries in astrophysics could reshape society in ways we cannot yet fully comprehend. As our understanding of the universe expands, so too does our understanding of our place within it. Fundamental questions about dark matter, black holes, and extraterrestrial life could lead to profound shifts in both philosophical and spiritual beliefs. As we unlock the secrets of the cosmos, our sense of identity as human beings, our purpose, our destiny, may be forever altered. Technological advancements born from astrophysical research also have the potential to drive significant societal progress. Innovations initially developed for studying distant stars and galaxies often find unexpected applications here on Earth, such as advancements in medical imaging, environmental monitoring, and telecommunications. These cross-disciplinary breakthroughs not only improve our quality of life, but also inspire the next generation of scientists and engineers. The pursuit of knowledge becomes a catalyst for economic growth, societal advancement, and the continuous evolution of human civilization. Moreover, the pursuit of space exploration fosters a spirit of global unity, transcending national boundaries and encouraging collaboration on an unprecedented scale. International space missions and joint research initiatives underscore the shared goals of humankind. These endeavors highlight the importance of nations working together toward a common purpose, a unity that can transcend political and cultural differences. As we collectively gaze toward the stars, this cooperation holds the potential to promote peace, bridging gaps between countries, and fostering a deeper sense of global community. Such collaborations can inspire greater conversations on tackling the planet's most pressing issues, such as climate change, resource depletion, and humanitarian crises. The same spirit that drives humanity to explore the cosmos can be harnessed to address challenges here on Earth. As we unlock the mysteries of the universe, there is a growing awareness of the profound responsibility we bear toward our planet. Discoveries that reveal the fragility of celestial bodies or the delicate balance of interstellar ecosystems prompt us to reassess our priorities. The realization that Earth is but a tiny oasis in the vast, infinite expanse of the universe deepens our respect for the planet. It urges us to adopt sustainable practices and focus on preserving the world for future generations. With every new discovery about distant planets, stars, and galaxies, we are reminded of the need to cherish and protect the unique environment that supports life on Earth. Public fascination with space exploration plays a pivotal role in shaping educational landscapes worldwide. When people express a sense of wonder and excitement about the cosmos, it resonates deeply within classrooms. Teachers and educational institutions recognize a prime opportunity to ignite the curiosity of the next generation of scientists, engineers, and informed citizens. Space exploration stirs imagination and wonder, encouraging schools to weave space-related themes into their curricula. From basic science lessons in elementary schools to more advanced courses in high school, the excitement about the cosmos translates into richer, more engaging educational experiences. One significant outcome of this growing interest is the expansion of STEM, science, technology, engineering, and mathematics programs. These fields are more crucial than ever, given their close ties to our understanding of space and the technologies that allow us to study it. Educational institutions often collaborate with space agencies, such as NASA, to develop teaching materials that align with ongoing space missions and discoveries. By drawing on real-world examples from space exploration, educators can help students connect classroom learning with the broader universe, enhancing the educational experience. Public events such as rocket launches and planetary exploration announcements often generate waves of enthusiasm about space. This collective excitement can lead to community-driven initiatives, such as public lectures, workshops, and hands-on activities like building model rockets or coding simulations. When communities engage in space-related projects, they cultivate a culture of scientific inquiry and exploration. This, in turn, influences the type of educational programs that emerge, emphasizing the importance of creativity, collaboration, and critical thinking. The advent of social media and online platforms has also revolutionized how space exploration is shared with the public. These platforms provide unprecedented access to space-related content, allowing information to be disseminated widely and rapidly. As a result, schools and educators can quickly incorporate the latest discoveries and trends into their lessons, keeping students at the forefront of scientific knowledge. In turn, this accessibility fosters a deeper passion for the sciences, inspiring students to dream big, think critically, and imagine contributing to humanity's ongoing quest to explore the cosmos. Equally important to the journey of space exploration is the preservation of celestial heritage. As we continue to reach further into space, the protection of key scientific and cultural sites takes on increasing importance. The study of celestial bodies, from planets and moons to asteroids, helps us uncover vital information about the origins and evolution of our solar system. By safeguarding these sites, we ensure that future generations have the opportunity to study them, furthering our understanding of humanity's place in the universe. The value of celestial heritage extends beyond scientific exploration. It also represents the legacy of human achievement in space. The locations we have studied, mapped, and explored are imbued with the marks of our curiosity and ambition. Whether it is the footprints left on the moon or the advanced technology enabling robotic probes to venture to the farthest reaches of space, these milestones serve as tangible symbols of human progress. They represent our collective drive to expand our knowledge, providing future generations with a historical record of our shared journey into the unknown. As humanity looks toward the future and considers the possibility of permanent habitation on other celestial bodies, the question of stewardship becomes increasingly urgent. With the commercialization of space and the potential for colonization of other worlds, it is vital to approach these new environments with respect and caution. This requires fostering an ethic of preservation that emphasizes scientific discovery while minimizing harm to these pristine landscapes. By safeguarding celestial environments, we aim to avoid the mistakes of the past, where exploitation of Earth's resources has often resulted in environmental degradation. The implications of preserving celestial heritage are far-reaching, intertwining our scientific endeavors with ethical considerations. They prompt us to reflect on our approach to exploring the cosmos. As we continue to venture beyond our planet, preserving the integrity of these celestial bodies not only enriches our understanding of the universe, but also serves as a reminder of our shared responsibility to protect the spaces we explore. In this way, we acknowledge our place within a much larger cosmic tapestry, inspiring future generations to approach space exploration with a mindset of stewardship and respect. Advancements in technology continue to transform our relationship with the universe, opening new frontiers in exploration. As we develop more advanced tools, our capacity to investigate the cosmos expands exponentially. What once seemed like the stuff of science fiction is rapidly becoming a reality. For example, powerful telescopes equipped with advanced imaging and data collection technologies enable us to peer further into space than ever before. These instruments reveal distant galaxies, exoplanets, and the remnants of cosmic events that shaped the universe billions of years ago, bringing us closer to understanding the mysteries of existence itself. With each technological breakthrough, we take another step toward unraveling the vast, awe-inspiring complexity of the cosmos. In the ever-evolving field of astrobiology, the quest to understand life beyond Earth has become an essential part of humanity's cosmic exploration. Armed with cutting-edge technologies, scientists are turning their gaze to distant worlds in search of answers. Mars, once a barren, red desert, is now at the forefront of this search. We are studying its surface, its geology, and its atmosphere, probing for evidence of ancient life, whether microbial or otherwise. At the same time, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are under intense scrutiny. Beneath their frozen exteriors, scientists believe there may be subsurface oceans, potentially harboring the conditions necessary for life. As we gather data from these faraway worlds, we are confronted with one of the most profound questions of existence. Are we truly alone in the universe? This search for life not only drives our exploration, but also fundamentally alters our perception of our place in the cosmos. The very act of reaching beyond our planet forces us to reconsider our origins, our evolution, and the vast interconnectedness of the universe. As we venture into space, we are reminded that we are part of something far greater than ourselves. Artificial intelligence is a critical partner in this endeavor. The sheer volume of data we collect from telescopes, satellites, and robotic probes is staggering. Processing and analyzing this data would be impossible without advanced AI systems, which sift through immense data sets to identify patterns, predict celestial events, and even detect phenomena that have yet to be fully understood by human minds. This symbiosis between technology and scientific inquiry is opening new frontiers in our understanding of the cosmos, revealing mysteries that once seemed beyond reach. As these technologies advance, the distinction between observer and participant becomes increasingly blurred. We are no longer passive recipients of cosmic data. Instead, we are active participants, using our technological prowess to engage with the universe in unprecedented ways. Whether through robotic exploration or future manned missions, humanity is slowly becoming part of the very fabric of the universe, experiencing firsthand the wonders and challenges of deep space. However, as we push further into the unknown, ethical questions begin to arise. The exploration of other worlds is not without its moral implications. How should we treat the environments and potential life forms we may encounter? Should we approach other planets with the same care we give to Earth, recognizing that they too are delicate ecosystems? These questions remind us that our exploration is not just about accumulating knowledge, but also about assuming responsibility for the preservation and respect of other worlds. Throughout history, missions to explore the cosmos have consistently pushed the boundaries of human knowledge. Each new discovery reveals not only the wonders of distant realms, but also critical lessons that shape future exploration efforts. One such lesson is the importance of collaboration. The success of missions like the Mars rovers and the Hubble Space Telescope demonstrates that great achievements in space exploration are often the result of collective efforts, with scientists, engineers, and experts from around the world coming together to solve complex problems. This global cooperation fosters innovation, allowing humanity to benefit from a rich tapestry of ideas and insights that cross national and cultural boundaries. Another key takeaway from past missions is the necessity of adaptability. Space exploration is fraught with uncertainties. Technical failures, environmental challenges, and unforeseen obstacles are commonplace. The Apollo missions to the Moon, the exploration of the outer planets, and even missions like the Voyager probes have all encountered unexpected hurdles. These experiences have taught us the value of building flexible systems that can adapt to changing circumstances. Future missions will likely focus on technologies that can respond to unexpected challenges in real time, optimizing performance and ensuring mission success despite the unpredictable nature of space. Risk management is another crucial lesson learned from past expeditions. Space missions are inherently risky, and failures along the way have provided valuable insights into what can go wrong. These lessons have helped scientists and engineers develop more robust protocols to protect both spacecraft and crew. By analyzing past failures, we can anticipate potential risks and mitigate them more effectively, paving the way for future missions that are both safer and more ambitious. Human space travel to Mars, once a distant dream, is now a real possibility thanks to the lessons learned from previous ventures into space. Perhaps one of the most pressing lessons is the importance of sustainability. As we look beyond Earth and consider the long-term prospects of space exploration, we must also think about the long-term preservation of the environments we encounter. How do we explore and use resources in space responsibly? How can we protect the pristine nature of other planets and moons, even as we seek to learn from them? Sustainability will play a central role in future space missions, guiding the way we interact with extraterrestrial environments and ensuring that exploration is conducted in a responsible, ethical manner. The universe is vast, and with each mission, we uncover more of its mysteries. Yet, there are still many anomalies that challenge our understanding of the cosmos. One of the most elusive is dark matter. Despite making up approximately 26% of the universe, dark matter remains invisible to our instruments. It does not interact with light or other forms of electromagnetic radiation, making it incredibly difficult to detect. The only evidence we have of its existence comes from its gravitational effects on visible matter. Theoretical models suggest that dark matter could be composed of particles that are yet to be discovered, prompting scientists to conduct experiments both underground and in space in an attempt to uncover its true nature. Fast radio bursts represent another cosmic enigma. These brief but powerful bursts of radio waves were first discovered in 2007, and their origins remain a mystery. Lasting just milliseconds, each burst releases an enormous amount of energy, equivalent to the total energy output of the sun over several days. Though many theories have been proposed to explain their source, including the possibility of pulsars or even signals from extraterrestrial civilizations, no definitive answer has emerged. This mystery continues to captivate astronomers, and each new burst detected adds to the growing puzzle. The Great Void, or KBC Void, adds to the list of cosmic anomalies. This vast region of space, which spans approximately 200 million light-years, contains far fewer galaxies than expected. Its existence challenges our understanding of how matter is distributed throughout the universe. Cosmologists are working to understand how such immense regions of emptiness can exist without violating the fundamental principles of cosmology, which predict a more uniform distribution of matter on large scales. Gravitational waves, ripples in space-time caused by massive cosmic events, such as the collision of black holes or neutron stars, represent another area of intense study. While the existence of gravitational waves has been confirmed, their full implications are still being explored. These waves offer scientists a new way to observe the universe, allowing us to study events that were previously invisible. The potential to learn more about the early universe, the nature of gravity, and the fabric of space-time itself is a thrilling prospect. As scientists continue to investigate these cosmic anomalies, the pursuit of knowledge takes on new dimensions. From mapping the distribution of galaxies to studying the nature of dark matter and gravitational waves, each discovery leads to new questions and possibilities. The mysteries of the universe may be vast, but the journey to unravel them is one of humanity's most exciting and important endeavors. Through collaboration, adaptability, and innovation, we are taking steps toward a deeper understanding of the cosmos, opening doors to a future where we can explore the universe in ways that were once unimaginable. Exploring cosmic voids holds profound implications for our understanding of dark energy, as well as the broader evolution of the universe. Dark energy, an enigmatic force believed to drive the accelerated expansion of the cosmos, is central to modern cosmology. Although it constitutes roughly 70% of the universe's energy content, its properties remain largely a mystery. By observing cosmic voids, vast, empty regions with extremely low mass density, scientists are able to glean vital information about how dark energy behaves in areas of minimal matter. These observations allow for the refinement of models that describe the universe's expansion, ultimately bringing us closer to understanding its ultimate fate. The study of voids intersects in fascinating ways with investigations into the cosmic microwave background, CMB, radiation, which is the faint afterglow from the Big Bang. This radiation provides a detailed snapshot of the universe when it was only a few 100,000 years old, offering invaluable insights into the conditions that existed during the universe's infancy. Understanding the formation and evolution of voids over billions of years gives us a clearer picture of how matter and energy interacted on the grandest scales, thus connecting the distant past of the universe to its present state. Through a combination of observational data and sophisticated simulations, researchers test and refine their hypotheses about void formation and behavior. These models allow for predictions on how voids will continue to evolve over time and their impact on galaxy formation. As galaxies interact with these voids, the dynamics of cosmic structures become clearer, shedding light on how matter has come together to form the universe we see today. Thus, exploring cosmic voids not only deepens our understanding of the universe's large-scale architecture, but also enhances our grasp of fundamental cosmological principles, such as dark energy. The study of the CMB also plays an indispensable role in this process. The cosmic background radiation is a remnant from the early universe, a faint glow scattered across the cosmos that provides a glimpse into the conditions just 380,000 years after the Big Bang. Despite being remarkably uniform, this radiation contains small, irregular fluctuations that reveal crucial information about the universe's structure and evolution. These fluctuations hint at regions of differing densities in the early universe, which would eventually give rise to galaxies and galaxy clusters. By analyzing these tiny variations, scientists can begin to determine the composition of the universe, how much of it consists of ordinary matter, and dark energy. Each fluctuation offers vital clues that help refine our models of how the universe evolved, providing a clearer picture of the forces that shaped cosmic history. Interestingly, some of the anomalies detected in the CMB have raised profound questions about the fundamental nature of the universe. Certain features appear to contradict the predictions made by the standard model of cosmology, sparking debates about whether new physics is needed to fully explain these observations. Far from being statistical, these anomalies challenge scientists to rethink the underlying conditions that led to the intricate structures we observe today. As technology continues to improve, our ability to detect and analyze these anomalies is advancing rapidly, promising to reveal even deeper insights into the universe's past and future. Each new discovery adds another piece to the grand puzzle of cosmic history, inviting a closer examination of the universe's origins and its eventual destiny. The continued exploration of cosmic voids and background radiation not only enhances our understanding of the universe's structure, but also opens new doors to the mysteries that still elude us. One of the most profound challenges in modern science is the quest to understand dark energy, an elusive force believed to account for the universe's accelerated expansion. With dark energy constituting roughly 70% of the cosmos, understanding its behavior is critical to predicting the universe's future. Scientists employ a range of observational techniques to investigate this mysterious force, blending the power of astronomical observation with theoretical physics. For instance, the study of distant supernovae has provided compelling evidence that the universe's expansion is not only continuing, but accelerating. These stellar explosions serve as cosmic yardsticks, allowing researchers to measure the distance to far-off galaxies and, by extension, the rate of expansion. This expanding universe appears to be propelled by dark energy, although the exact mechanisms remain unclear. Another key tool in this investigation is the cosmic microwave background radiation, which offers a wealth of information about the early universe and its subsequent evolution. By studying the fluctuations in this radiation, scientists can infer the density of dark energy and understand how it has influenced the universe's expansion over time. Data from missions such as the Planck spacecraft have been instrumental in refining our understanding of the universe's composition, helping to shed light on the elusive properties of dark energy. Gravitational lensing is also a crucial method in the study of dark energy. When light from distant galaxies passes near massive objects, the light is bent due to the gravitational pull of these objects. This effect allows researchers to map the distribution of both dark and visible matter in the universe. By examining the distortions in light caused by gravitational lensing, scientists can uncover new insights into how dark energy impacts the formation and evolution of large-scale cosmic structures. As technology continues to advance, future telescopes and observatories will enhance our ability to measure the properties of the universe, offering even more precise insights into the nature of dark energy. By combining new data with evolving theories, scientists are increasingly positioned to unravel the mysteries of dark energy, which could ultimately provide answers to some of the most fundamental questions about the universe's fate. In addition to cosmological studies, the field of quantum mechanics is poised to further reshape our understanding of reality. Phenomena such as quantum entanglement and superposition challenge traditional notions of space and time. In entanglement, particles become linked in such a way that the state of one particle instantaneously affects the state of another, regardless of distance between them. These strange phenomena suggest that our classical perception of space, separation, and individuality may be illusory, prompting scientists to rethink the very foundations of reality. Moreover, advancements in cosmology could lead to groundbreaking discoveries about the nature of dark matter and dark energy, two mysterious components believed to make up about 95% of the universe's total energy density. Although these forces remain elusive, uncovering their properties is key to understanding the cosmos, from galaxy formation to the very fate of the universe. Neuroscience, too, holds the potential for transformative discoveries. As scientists explore the intricacies of the human brain, they may uncover the underlying mechanisms of consciousness and perception. This could lead to a complete redefinition of how we interpret our experiences of reality, suggesting that consciousness may not be merely a byproduct of neural activity, but an inherent aspect of existence itself, linked to the fabric of the universe. Finally, the convergence of artificial intelligence and human cognition could offer a new dimension of reality altogether. If breakthroughs in AI enable us to merge human thought processes with machine intelligence, we may find ourselves questioning the very nature of intelligence, existence, and even life itself. Such advancements would challenge our current definitions of what it means to be alive or conscious, offering the potential for a radically different understanding of reality. Each of these scientific avenues, ranging from the depths of the cosmos to the intricacies of quantum mechanics and neuroscience, holds the promise of revolutionary discoveries. Together, they invite us to rethink the very fabric of reality, offering glimpses into a universe far more mysterious and interconnected than we have ever imagined. The quest to uncover these mysteries is just beginning, and the potential for transformative discoveries is boundless.